Welcome back to Science Sleep Stories. Tonight we're embarking on a journey through our cosmic neighbourhood, a journey that spans billions of years and millions of miles. We're going to explore the solar system, that magnificent collection of worlds spinning around our star, each one a universe unto itself, each one carrying secrets from the dawn of time. Before we drift into the depths of space, take a moment to get comfortable. Adjust your pillows, pull up that blanket, maybe dim the lights, or turn on a soft fan for that gentle background hum. And if you enjoy these cosmic voyages we take together, consider liking this video and subscribing to the channel. It really helps us continue creating these relaxing explorations of science and space. Let me know in the comments where you're tuning in from tonight and what fascinates you most about our solar system. Now, close your eyes if you'd like, or simply let your gaze soften. Let the weight of the day slip away as we prepare to travel through space and time. Tonight isn't about memorizing facts or passing a test. This is about wonder, about understanding our place in the cosmos, about finding peace in the vast mechanical ballet that has been unfolding above our heads for 4.5 billion years, the solar system. Just speaking those words conjures images, doesn't it? The rings of Saturn catching the sunlight, the great red spot churning on Jupiter's face, the barren, cratered surface of Mercury baking under an unforgiving sun. Mars, rust-red and distant, holding on to secrets buried beneath its dusty surface, and Earth, our blue marble, suspended in the velvet black, the only place in the known universe where life thrives in such magnificent abundance. But the solar system is more than just a collection of planets. It's a family, a system born from chaos, sculpted by gravity, and refined over eons into the elegant configuration we observe today. It's 8 major planets, 5 officially recognized dwarf planets, hundreds of moons, thousands of asteroids, millions of comets, and countless particles of dust and ice, all bound together by the gravitational embrace of our Sun. The scale of it all can be difficult to grasp. If you could somehow shrink the solar system down so that the Sun was the size of a basketball, Earth would be smaller than a peppercorn, sitting about 26 feet away. Neptune, the most distant major planet, would be a pinhead more than half a mile away, and the Oort cloud, that distant shell of icy bodies at the very edge of the Sun's gravitational influence, would extend for nearly 30 miles in every direction. The solar system is mostly empty space, punctuated by worlds that, despite their enormous size, are tiny compared to the distances between them. Yet despite this emptiness, despite these vast gulfs of nothing, the solar system is a dynamic, interconnected place. The Sun's light takes 8 minutes to reach Earth, but it warms our world and powers the weather systems that shape our climate. Jupiter's massive gravity acts like a cosmic vacuum cleaner, deflecting asteroids and comets that might otherwise threaten the inner planets. Saturn's rings, those delicate bands of ice and rock, are shepherded by dozens of tiny moons, each one carving gaps and maintaining the intricate structure through gravitational influence. The solar system is not a museum of static displays. It's a living system, constantly changing, constantly evolving. Tonight, we're going to explore this system from the inside out. We'll begin at the very beginning, with the birth of the solar system itself, watching as a cloud of gas and dust collapses under its own gravity, igniting a star and spawning a family of worlds. We'll visit the Sun, that brilliant nuclear furnace at the centre of everything, understanding how it works and why it matters. Then we'll journey outward, planet by planet, moon by moon, exploring each world's unique characteristics, its mysteries, its beauty. We'll stand on Mercury's scorched surface, where the Sun looms 3 times larger than it appears from Earth, and where temperatures can swing by more than 1,000 degrees between day and night. We'll peer through the thick sulfuric clouds of Venus, down to a surface hot enough to melt lead, where the atmospheric pressure would crush you like an empty soda can. We'll appreciate Earth, our home, with its liquid water oceans, its protective magnetic field, and its blanket of life-giving atmosphere. We'll walk the rust-coloured plains of Mars, where ancient riverbeds tell stories of a wetter, warmer past. We'll navigate through the asteroid belt, that debris field between the rocky inner planets and the gas giants beyond, where millions of objects orbit in a cosmic traffic jam that's actually far more empty than it appears in movies. We'll witness the majesty of Jupiter, the king of planets, a gas giant so large it could swallow all the other planets combined, its great red spot a storm larger than Earth that has raged for centuries. We'll marvel at Saturn and its stunning ring system, those billions upon billions of particles of ice catching and reflecting sunlight, creating one of the most beautiful sights in the solar system. We'll venture into the deep outer realm, visiting the ice giants Uranus and Neptune, worlds of frigid methane clouds and supersonic winds, so distant that the sun appears as little more than a bright star in their skies. And finally, we'll journey to the edge, to the Kuiper Belt and beyond, where Pluto and countless other icy worlds orbit in the cold and dark, remnants from the solar system's formation, time capsules waiting to tell their stories to patient explorers. This is a journey measured not in miles but in astronomical units, where 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. It's a journey that humans have only just begun to make, sending robotic emissaries to be our eyes and ears to touch these distant worlds on our behalf, to bring back images and data that transform these points of light in our telescopes into real places as tangible and complex as the ground beneath your feet. So settle in. Let the gentle rhythm of this cosmic tour lull you into a peaceful state. Let your mind wander among the planets, imagining the view from their surfaces, picturing their moons rising over alien horizons. The solar system is your home on a grander scale, and tonight you're going to understand it better than ever before. Our story begins 4,600,000,000 years ago, give or take a few million years. The universe itself was already more than 9 billion years old by this point, ancient beyond comprehension, already filled with billions of galaxies, each containing billions of stars. But in one particular corner of one particular galaxy, a spiral arm of the Milky Way about 26,000 light-years from the galactic centre, something new was about to happen. There, in the cold reaches of interstellar space, floated a giant molecular cloud. It was enormous, perhaps several light-years across, a dark nebula of gas and dust so thick that if you could somehow stand inside it, you wouldn't be able to see stars in any direction. This cloud was cold, just a few degrees above absolute zero, and it was mostly hydrogen, the simplest and most abundant element in the universe. But mixed in with that hydrogen was helium, and traces of heavier elements, carbon, oxygen, iron, silicon, elements forged in the nuclear furnaces of previous generations of stars and scattered into space when those stars died. This cloud had been drifting through space for millions of years, perhaps billions, slowly growing as it accumulated more gas and dust from the interstellar medium. It was stable, held together by its own feeble gravity, but not collapsing, not changing, just existing in the dark between the stars, until something disturbed it. We don't know for certain what triggered the collapse. Some scientists think a nearby supernova, the violent death of a massive star, sent a shockwave racing through the region, compressing the molecular cloud and starting the process. Others believe it might have been the gravitational influence of a passing star, or perhaps just a random fluctuation in the cloud's density that reached a tipping point. Whatever the cause, once the collapse began, there was no stopping it. Gravity, that patient, inexorable force, began pulling the cloud in on itself. As it contracted, it began to spin just a little at first, but faster and faster as it shrank, like an ice skater pulling in her arms during a spin. This is conservation of angular momentum, one of the fundamental laws of physics, and it meant that as the cloud collapsed, it couldn't remain spherical. Instead, it flattened into a disk, with most of the material falling toward the centre, but some of it spreading out into an enormous, rotating pancake of gas and dust. This disk, this protoplanetary disk, was where our solar system would be born. At the centre, where the density was highest and the temperature was rising, a protosun was forming. The pressure at the core was building, atoms were being squeezed together, and the temperature was climbing into the millions of degrees. And then, about 4,550,000,000 years ago, something remarkable happened. The pressure and temperature at the core of the protosun reached a critical threshold, and hydrogen atoms began to fuse into helium, releasing tremendous amounts of energy in the process. The sun ignited. Let there be light. The newborn sun was a violent, unstable object, nothing like the steady, predictable star we know today. It blazed with energy, sending out powerful stellar winds and intense bursts of radiation that swept through the protoplanetary disk, clearing away most of the remaining gas, and leaving behind only the solid particles of dust and ice. This early phase, sometimes called the T-Tauri phase, after a similar young star we can observe today, lasted perhaps a few million years, a blink of an eye in cosmic terms. But while the sun was undergoing its turbulent childhood, something equally remarkable was happening in the disk around it. The dust particles, tiny specks of rock and ice, were colliding with each other. Most of the time, these collisions were gentle enough that the particles stuck together rather than bouncing apart. This process, called accretion, started small, with dust grains no bigger than smoke particles clumping together into pebbles. The pebbles collided and formed rocks. The rocks collided and formed boulders. The boulders formed objects the size of mountains, then moons, then planets. Near the sun, where temperatures were highest, only materials with high melting points could survive. Rock and metal condensed out of the disk, forming the ingredients for the terrestrial planets. Water, methane, and ammonia evaporated in the heat and were driven outward by the sun's radiation. Farther out beyond what's now called the frost line, about 3 to 4 astronomical units from the sun, temperatures were low enough for ice to form. This meant there was far more solid material available in the outer disk, and the planets that formed there could grow much larger. The process wasn't smooth or uniform. The early solar system was a chaotic, violent place. The disk was full of planetesimals, objects ranging from a few kilometres to a few hundred kilometres across, all orbiting the sun and frequently colliding with each other. Some collisions were gentle and resulted in mergers, building larger and larger bodies. Other collisions were catastrophic, shattering both objects into fragments that had to start the accretion process all over again. Over millions of years, certain objects began to dominate their orbital zones. These were the planetary embryos, protoplanets with enough mass that their gravity began to significantly influence nearby objects. They swept up smaller planetesimals like cosmic vacuum cleaners, growing larger and larger. In the inner solar system, 4 such embryos emerged, the ancestors of Mercury, Venus, Earth, and Mars. In the outer solar system, where there was more material to work with, truly massive embryos formed. These were the cores of Jupiter, Saturn, Uranus, and Neptune. Jupiter formed first among the giants, and it formed quickly. Its core grew so massive, perhaps 10 to 15 times the mass of Earth, that it was able to gravitationally capture hydrogen and helium directly from the protoplanetary disk before the sun's radiation could blow it all away. Jupiter grew into a monster, eventually accumulating more than 300 times Earth's mass, more than twice as massive as all the other planets combined. Its presence in the outer solar system had profound consequences. Its immense gravity stirred up the orbits of other objects, flinging some inward toward the sun and others outward into the darkness beyond. Saturn formed slightly later and couldn't capture quite as much gas, ending up about a third of Jupiter's mass. Uranus and Neptune formed even later and even farther out, where the disk was more sparse and the accretion process was slower. They managed to capture some hydrogen and helium, but not nearly as much as Jupiter and Saturn, which is why they're often called ice giants rather than gas giants. Their interiors are thought to be mostly water, methane and ammonia ices surrounding rocky cores. The formation of the terrestrial planets took longer and was more violent. Earth, for instance, went through numerous collisions with other planetary embryos during its formation. The most spectacular of these occurred perhaps 50 million years after the Sun's formation, when an object about the size of Mars, sometimes called Theia, slammed into the proto-Earth in a glancing blow. The impact was so violent that it vaporized Theia and much of Earth's outer layers, sending huge amounts of material into orbit around Earth. This debris quickly coalesced into a new body, our Moon. The giant impact hypothesis, as it's called, explains many of the Moon's unusual characteristics, including why its composition is similar to Earth's mantle, but it has almost no iron core. Mars formed farther out and had a different history. It grew more slowly than Earth and never quite reached the same size. Some scientists think Jupiter's powerful gravity stirred up the asteroid belt region so much that it prevented Mars from accumulating as much material as it otherwise might have. This left Mars as a somewhat undersized planet, about half the diameter and 1/10 the mass of Earth. As the planets were forming, the leftover planetesimals and debris didn't just disappear. Some of it remained in stable orbits between the planets, forming what we now call the asteroid belt between Mars and Jupiter. Other objects were captured by the planets as moons. Still others were flung into the outer solar system, forming the Kuiper Belt beyond Neptune and the even more distant Oort cloud, vast reservoirs of comets that mark the outermost boundary of the Sun's gravitational influence. The final stages of planetary formation were marked by a period called the Late Heavy Bombardment, which occurred about 4 billion to 3 billion, 800 million years ago. During this time, there was a surge of impacts throughout the inner solar system as Jupiter and Saturn settled into a particular orbital resonance that destabilized many objects in the outer solar system and sent them careening inward. The Moon's heavily cratered surface is a record of this violent period. Earth was bombarded too, but geological processes have erased most of the evidence. After the late heavy bombardment ended, the solar system began to settle into a more stable configuration. The planets cleared their orbital zones of most remaining debris. The Sun stabilized into the steady, middle-aged star we know today. The violent chaos of formation gave way to the relatively peaceful, predictable clockwork that has persisted for the past 3.5 billion years. But the formation process left clues scattered throughout the solar system. The asteroid belt is a graveyard of failed planets, objects that never managed to accumulate into a single large body because of Jupiter's disruptive influence. The Kuiper Belt and Oort cloud are time capsules, preserving icy planetesimals virtually unchanged from the solar system's youth. Comets, which occasionally fall in toward the Sun from these distant reservoirs, bring pristine samples of the original protoplanetary disk. Meteorites that fall to Earth carry in them presolar grains, tiny crystals older than the solar system itself, remnants of the molecular cloud from which everything formed. By studying these clues, by examining the compositions and orbits of solar system objects, by modelling the physics of disk collapse and planetary accretion on supercomputers, scientists have been able to piece together this story of the solar system's birth. It's a story written in mathematics and verified by observation, a story that explains not just how our solar system came to be, but potentially how planetary systems around other stars form as well. The Sun and planets are not eternal. They had a beginning, and they will have an end. But in the 4.5 billion years since that molecular cloud collapsed, since that proto-sun ignited, since those first planetesimals collided and merged, the solar system has been our home. It's the stage on which the entire story of life on Earth has unfolded. And now, as we send our spacecraft out to explore this system, we're learning to read that story, to understand where we came from and where we might be going. At the centre of everything, blazing with the light of 1 billion fusion reactions occurring every second, sits the Sun. It's easy to take it for granted, that bright disk in the sky that rises each morning and sets each evening. But the Sun is extraordinary, a sphere of plasma more than 100 times wider than Earth, so massive that it contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids and comets, all the dust and gas, all of it together makes up less than 1/5 of 1% of the solar system's total mass. The Sun is not just at the centre of the solar system. In a very real sense, the Sun is the solar system. Let's start with the basics. The Sun is a star, a main sequence star of spectral type G2V, sometimes called a yellow dwarf, though it's neither particularly yellow nor particularly dwarf-like. It's actually quite average, more massive and more luminous than about 85% of stars in the galaxy, but far smaller and dimmer than the really massive hot stars that blaze briefly before exploding as supernovae. The Sun is about 4,600,000,000 years old, roughly middle-aged for a star of its type, and it has approximately another 5 billion years of stable hydrogen burning ahead of it before it begins to change in more dramatic ways. The Sun's diameter is about 1,392,000 kilometres, or 864,000 miles. To put that in perspective, you could line up 109 Earths side by side across the Sun's face. If the Sun were hollow, you could fit about 1.3 million Earths inside it. But the Sun is not hollow. It's a ball of plasma, mostly hydrogen and helium, heated to such extreme temperatures that atoms cannot hold on to their electrons. Everything is ionized, a soup of positively charged nuclei and negatively charged electrons all mixed together, held in place by the Sun's immense gravity. The Sun's mass is approximately 2 times 10 to the power of 30 kilograms, or about 330,000 times the mass of Earth. This enormous mass creates enormous gravitational pull, and it's this gravity that holds the solar system together, that keeps the planets in their orbits, that prevents the Sun itself from flying apart. But gravity also creates pressure, and in the Sun's core, where the weight of all the overlying layers presses down, the pressure is about 250 billion times Earth's atmospheric pressure at sea level. Under such pressure, matter behaves in extraordinary ways. The temperature in the core is about 15 million degrees Celsius, or 27 million degrees Fahrenheit. At these temperatures, hydrogen nuclei, which are just single protons, are moving so fast that when they collide they can overcome the electrostatic repulsion that normally keeps positively charged particles apart. They fuse, combining to form helium nuclei in a process that releases energy according to Einstein's famous equation E=mc². A tiny amount of mass is converted into a tremendous amount of energy, and this energy is what makes the Sun shine. The fusion process in the Sun's core is actually a multi-step reaction called the proton-proton chain. First, 2 protons collide with enough energy to fuse, forming a deuterium nucleus, a positron, and a neutrino. The positron quickly annihilates with an electron, releasing more energy. Then the deuterium nucleus fuses with another proton, forming helium-3 and releasing a gamma-ray photon. Finally, 2 helium-3 nuclei fuse to form helium-4, releasing 2 protons back into the mix. The net result is that 4 hydrogen nuclei are converted into 1 helium nucleus, 2 protons are recycled, and a tremendous amount of energy is released. Every second, the Sun converts about 600 million tons of hydrogen into helium. Every second, about 4 million tons of matter is converted directly into energy. That energy, in the form of high-energy gamma-ray photons and neutrinos, starts its journey outward from the core. The neutrinos, which barely interact with matter at all, escape almost immediately, passing through the Sun and out into space at the speed of light. Some of them pass through Earth, billions of them streaming through your body every second without you ever noticing. The photons have a very different journey. A photon created in the Sun's core will collide with a particle of plasma almost immediately, being absorbed and re-emitted in a random direction. It will collide again and again, millions upon millions of times, following a drunkard's walk through the dense plasma of the Sun's interior. This region, from the core out to about 70% of the Sun's radius, is called the radiative zone. Here, energy is transported primarily by radiation, by these countless absorptions and emissions of photons. The journey through the radiative zone takes a long time. The typical photon might take something like 100,000 years to random walk its way from the core to the upper edge of the radiative zone. By the time it gets there, it's been absorbed and re-emitted so many times that its energy has been degraded. The high-energy gamma rays from the core have become lower-energy X-rays, then ultraviolet photons, then visible light. At about 70% of the Sun's radius, the character of the Sun's interior changes. The temperature has dropped to about 2 million degrees Celsius, cool enough that plasma begins to behave differently. Convection becomes more efficient than radiation at transporting energy, and the outer 30% of the Sun's interior, the convective zone, is a seething, roiling mass of rising hot plasma and sinking cool plasma. Think of it like a pot of boiling water, but on a scale almost incomprehensible. Individual convective cells might be hundreds or thousands of kilometers across, and they carry enormous amounts of energy upward. The top of the convective zone is the photosphere, the visible surface of the Sun, the layer that emits the light we see. The photosphere is relatively thin, just a few hundred kilometers deep, but it's where the Sun's density drops low enough that photons can finally escape into space without immediately being reabsorbed. The temperature at the photosphere is about 5,500 degrees Celsius, much cooler than the core or even the base of the convective zone. This is why the Sun appears yellow to our eyes. If we could see the core directly, it would appear blue-white, shifted toward higher energies. The photosphere is not uniform. Observations through telescopes reveal a granular structure, a pattern of bright cells surrounded by darker lanes. Each bright cell is the top of a convective column of rising hot plasma, and the dark lanes are cooler plasma sinking back down. Individual granules might be about 1,000 kilometers across and last for about 20 minutes before the convection pattern shifts. There are also larger structures called supergranules, tens of thousands of kilometers across, that represent a larger scale of convection. And superimposed on all this are sunspots, dark regions that appear in the photosphere when strong magnetic fields suppress convection, cooling the surface by about 1,500 degrees and making it appear dark by contrast. Sunspots are fascinating because they're windows into the Sun's magnetic field, and the Sun's magnetic field is anything but simple. The Sun doesn't have a simple dipole field like Earth does. Instead, it has a complex, tangled magnetic field that's generated by the motion of charged plasma in the convective zone, a process called the solar dynamo. Magnetic field lines emerge from the Sun's interior, loop through the atmosphere and plunge back down somewhere else. Sunspots mark where these field lines pierce the photosphere. The number of sunspots on the Sun varies in a roughly 11-year cycle, from solar minimum, when there might be days or weeks with no sunspots at all, to solar maximum, when dozens of sunspots might be visible simultaneously. This solar cycle is accompanied by changes in the Sun's activity. During solar maximum, the Sun experiences more frequent and intense eruptions, including solar flares and coronal mass ejections, events that can send billions of tons of plasma hurtling out into space at speeds of hundreds of kilometers per second. Above the photosphere lies the Sun's atmosphere. The chromosphere, a layer a few thousand kilometers thick, is slightly hotter than the photosphere, ranging from about 4,000 to 20,000 degrees Celsius. It's visible during total solar eclipses as a reddish ring around the Moon's silhouette, the red colour coming from hydrogen emission. Above the chromosphere is the corona, the Sun's outer atmosphere, and this is where things get really strange. The corona is incredibly hot, more than 1 million degrees Celsius, and in some regions as hot as 3 million degrees. This is the coronal heating problem, one of the big unsolved mysteries in solar physics. How does the corona, farther from the source of energy in the core, end up hotter than the photosphere? The answer seems to involve magnetic fields. The tangled, constantly shifting magnetic field lines in the corona can snap and reconnect, converting magnetic energy into heat. Waves of energy travelling along magnetic field lines might also contribute. Despite decades of study and increasingly sophisticated spacecraft observations, scientists are still working out the exact mechanisms. The corona extends far out into space, gradually thinning until it merges with the solar wind, a constant stream of charged particles, mostly protons and electrons, flowing outward from the Sun in all directions. The solar wind fills the solar system, creating a bubble called the heliosphere that extends well beyond the orbits of the planets. It's the solar wind that causes comets to develop tails that always point away from the Sun, regardless of the comet's direction of motion. It's the solar wind that interacts with Earth's magnetic field, funneling particles down toward the poles and creating the auroras, those shimmering curtains of light in the Arctic and Antarctic skies. The Sun's energy output is staggering. Every second, the Sun radiates about 3.8 times 10 to the power of 26 watts of power, or 3.8 times 10 to the power of 33 ergs per second if you prefer the older units. To put this in perspective, the Sun produces more energy in 1 second than all of human civilization has produced in its entire history. A single second of the Sun's output could power all of human civilization at current energy consumption rates for about 500,000 years. Only a tiny fraction of this energy reaches Earth. Earth's distance from the Sun, about 150 million kilometers, or 93 million miles, means that we intercept only about 1/2 billionth of the Sun's total energy output. But that tiny fraction, about 1,370 watts per square metre, at the top of Earth's atmosphere, is enough to power the entire biosphere. The Sun's energy drives photosynthesis in plants and phytoplankton, producing the oxygen we breathe and the food we eat. It drives weather systems, evaporating water from the oceans and carrying it over the continents as rain. It creates temperature differences that drive winds and ocean currents. Without the Sun, Earth would be a frozen, lifeless ball of rock. The average temperature would be around negative 270 degrees Celsius, just a few degrees above absolute zero, cold enough that the atmosphere would condense and freeze. There would be no liquid water, no weather, no seasons, no life. Everything that makes Earth habitable exists because of the steady stream of energy from our star. But the Sun will not shine forever. In about 5 billion years, the hydrogen in the Sun's core will be exhausted. Without hydrogen fusion to create outward pressure, the core will begin to contract under its own gravity. As it contracts, it will heat up, eventually becoming hot enough to fuse helium into carbon and oxygen. But this helium fusion will produce even more energy than hydrogen fusion, and the outer layers of the Sun will expand dramatically. The Sun will become a red giant swelling to perhaps 260 times its current diameter, large enough to engulf the orbits of Mercury and Venus, and possibly Earth as well. The red giant phase will last for about 1 billion years. During this time, the Sun will be far cooler at its surface than it is today, glowing with a dull red colour, but it will be so much larger that it will actually be brighter overall. Eventually, the helium in the core will be exhausted too, and without a source of energy to support the outer layers, they will drift away into space, forming a planetary nebula, a beautiful expanding shell of glowing gas. All that will remain is the Sun's hot, dense core, a white dwarf about the size of Earth but containing about half the Sun's current mass. This white dwarf will slowly cool over trillions of years, eventually fading to a cold, dark sphere, a stellar corpse. But that's billions of years in the future. For now, the Sun is stable, reliable, pouring out its steady stream of light and warmth. It's been doing this for 4.5 billion years, and it will continue doing this for billions more. The Sun is not just a ball of fusing hydrogen, it's the reason we exist, the source of almost all the energy that powers life on Earth, the gravitational anchor that holds the solar system together. It's our star, and we are, quite literally, made of star stuff. Atoms forged in the cores of previous generations of stars and gathered together by gravity to form the sun and planets. When you feel the sun's warmth on your face, you're feeling the touch of nuclear fusion, the fundamental process that lights up the universe. Let's begin our journey through the planets with the closest one to the sun, the small, swift, mysterious world called Mercury. Named after the Roman messenger god who moved swiftly on winged sandals, Mercury is appropriately fleet. It races around the sun faster than any other planet, completing an orbit in just 88 Earth days, travelling through space at nearly 48 kilometers per second, or about 107,000 miles per hour. Mercury is small, the smallest of the 8 major planets, just slightly larger than our Moon. Its diameter is about 4,880 kilometers, or 3,032 miles, which makes it about 38% the diameter of Earth. If you could hold Mercury and Earth side by side, Mercury would look like a baseball next to a basketball. Despite being larger than our Moon, Mercury and the Moon share a striking resemblance, at least from a distance. Both are airless, heavily cratered worlds covered in regolith, a fine powder of pulverized rock created by billions of years of meteorite impacts. But while Mercury and the Moon may look similar, Mercury's relationship with the Sun makes it an entirely different beast. Mercury orbits at an average distance of about 58 million kilometers, or 36 million miles from the Sun. This is only about 38% of the distance from Earth to the Sun. At this proximity, the Sun's apparent size in Mercury's sky is about 3 times larger than it appears from Earth. The Sun's energy is more than 6 times more intense. Mercury basks, or rather bakes, in a flood of radiation that would be utterly lethal to any Earth life. The temperatures on Mercury are extreme, some of the most extreme in the entire solar system. During Mercury's day, when the Sun is high in the sky, surface temperatures can climb to about 430 degrees Celsius, or 800 degrees Fahrenheit. This is hot enough to melt lead, hot enough to melt tin and zinc. The rocks themselves don't quite melt, but they come frighteningly close, and any exposed surface glows dully in the infrared, radiating heat back into space as fast as it can. But Mercury's nights are equally extreme in the opposite direction. Because Mercury has essentially no atmosphere, there's nothing to trap heat or moderate temperatures. As soon as the sun sets, temperatures plunge. By the time the long night reaches its coldest, just before dawn, surface temperatures can drop to about negative 180 degrees Celsius, or negative 290 degrees Fahrenheit. This is a temperature swing of more than 600 degrees Celsius, over 1,000 degrees Fahrenheit, between day and night. Mercury holds the record for the greatest temperature variation of any planet in the solar system. This temperature swing happens because Mercury's rotation is peculiar. For a long time, astronomers thought Mercury was tidally locked to the Sun, always keeping the same face toward it the way the Moon keeps the same face toward Earth. But radar observations in the 1960s revealed something stranger. Mercury rotates on its axis once every 58.65 Earth days, and it orbits the Sun once every 88 Earth days. These numbers are in a 3-to-2 resonance, meaning Mercury rotates exactly 3 times for every 2 orbits around the Sun. This resonance creates a bizarre day-night cycle. If you could stand on Mercury's surface, you would experience one full day-night cycle, from sunrise to sunrise, in 176 Earth days, exactly 2 Mercurian years. The Sun would move very slowly across the sky, taking 88 Earth days to go from horizon to horizon. And because Mercury's orbit is quite elliptical, the Sun's motion would not be uniform. Near perihelion, the closest point to the Sun, Mercury's orbital speed exceeds its rotational speed, and the Sun would actually appear to move backward in the sky for a few Earth days, rising, stopping, setting a little bit, then rising again before continuing its journey across the sky. Mercury's lack of atmosphere is not an accident. Any atmosphere it might have had when it formed has long since been stripped away. Mercury's small size means it has weak gravity, only about 38% of Earth's surface gravity. This weak gravity cannot hold on to gas molecules, especially when those molecules are being heated to high speeds by the intense solar radiation. The solar wind, that stream of charged particles flowing outward from the Sun, constantly bombards Mercury, and without a thick atmosphere or a strong magnetic field to deflect it, the solar wind strips away any gases that outgas from the surface. Mercury does have an extremely tenuous exosphere, barely worthy of the name atmosphere. This exosphere consists of atoms blasted off the surface by solar wind and micrometeorite impacts, atoms that briefly hover above the surface before either escaping into space or falling back down. The exosphere contains oxygen, sodium, hydrogen, helium, potassium, calcium, and a few other elements, but the total pressure at the surface is less than a trillionth of Earth's atmospheric pressure. You could not breathe this exosphere. You couldn't even detect it without sophisticated instruments. Surprisingly, Mercury has a global magnetic field, something scientists did not expect for such a small planet. Earth's magnetic field is generated by a dynamo effect in its molten iron core, but Mercury is so small that scientists thought its core should have cooled and solidified long ago. Yet the Mariner 10 and Messenger spacecraft measured a definite magnetic field, about 1% the strength of Earth's field, but still a proper dipole field aligned roughly with Mercury's rotation axis. The presence of this magnetic field suggests that at least part of Mercury's core is still liquid. Mercury has an enormous iron core, about 85% of the planet's radius, and containing about 70% of its mass. This is a far larger proportion than any other terrestrial planet. Earth's core is only about 15% of its volume. Mercury's core is so large that the rocky mantle and crust surrounding it are only about 400 kilometers thick, thinner than the distance from Los Angeles to San Francisco. Why does Mercury have such a large core? The answer is not entirely clear, but there are a few theories. One possibility is that Mercury formed from material in the solar nebula that was naturally rich in iron relative to silicate rock. Another possibility is that a giant impact early in Mercury's history blasted away much of the planet's rocky mantle, leaving the iron core disproportionately intact. Evidence from Mercury's surface, composition, measured by the Messenger spacecraft suggests that the second scenario might be more likely. Mercury's surface is heavily cratered, a testament to billions of years of bombardment by asteroids and comets. The largest crater, Caloris Basin, is about 1,550 kilometers across, one of the largest impact basins in the solar system. The impact that created Caloris was so violent that it sent shock waves through the entire planet. On the opposite side of Mercury from Caloris, there's a region of jumbled hilly terrain thought to have been created when seismic waves from the Caloris impact converged and disrupted the surface. Between the craters, much of Mercury's surface is covered by smooth plains, areas that appear to have been resurfaced by volcanic activity billions of years ago. These plains are similar in some ways to the Luna Maria, the dark basaltic plains on the Moon, but Mercury's volcanic history seems to have been less extensive. The planet cooled and became geologically inactive relatively early in its history. Mercury's surface also features long, winding cliffs called lobate scarps. These scarps can be hundreds of kilometers long and up to 3 kilometers high, and they formed when Mercury's interior cooled and contracted, causing the crust to buckle and fracture. The entire planet appears to have shrunk by about 7 kilometers in radius over its history, and the lobate scarps are the wrinkles left behind by that shrinkage. One of the most unexpected discoveries about Mercury came from radar observations of its poles. The poles of Mercury, because of the planet's very small axial tilt, have deep craters that never see sunlight. The floors of these permanently shadowed craters remain cold, never warming above about -180 degrees Celsius. And in these cold traps, radar revealed bright, highly reflective deposits that are almost certainly water ice. Water ice on Mercury, the closest planet to the Sun, seems paradoxical, but the permanently shadowed craters provide a cold enough refuge for ice to survive. The ice probably came from comets that impacted Mercury over billions of years. When a comet struck the sun-baked surface, most of its water vaporized, but some of the vapor migrated to the poles and became trapped in the shadowed craters, where it has remained ever since. Some estimates suggest there could be 100 million to 1 trillion kilograms of water ice at Mercury's poles, buried under a layer of darker material that may be organic-rich compounds also delivered by comets. Mercury has been visited by 2 spacecraft, NASA's Mariner 10, which flew by 3 times in the mid-1970s, and NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger, short for Mercury surface, space environment, geochemistry and ranging, provided the first comprehensive look at this enigmatic world, mapping the entire surface, measuring the composition of the rocks, characterizing the magnetic field and exosphere, and revealing Mercury to be far more complex and interesting than anyone had expected. Mercury remains a world of extremes, a place where the sun dominates the sky and the environment, where temperatures swing wildly and the surface is alternately roasted and frozen. It's a small world, but it's a world that holds clues to the solar system's formation, clues locked in its oversized core, its ancient cratered surface, and its unexpected pockets of polar ice. Mercury is not a hospitable place, but it's a fascinating one, and it's a reminder that even the smallest and most overlooked members of the solar system have stories to tell. If you look into the western sky just after sunset or into the eastern sky just before sunrise, you'll often see a brilliant point of white light, brighter than any star, brighter even than Jupiter. That's Venus, Earth's nearest planetary neighbour, shining with reflected sunlight filtered through its thick atmosphere. The ancient Greeks called it Phosphorus and Hesperus, not realising they were the same object. The Romans called it Venus, after their goddess of love and beauty, and the name stuck. Venus, the evening star, the morning star, the most beautiful light in the heavens. But Venus, for all its beauty from a distance, is hell up close. Of all the planets in the solar system, Venus might be the most inhospitable, the most utterly lethal to any form of Earth life. It's a cautionary tale, a reminder that appearances can be deceiving, that a planet similar in size and composition to Earth can follow a very different path. Venus is Earth's twin in many ways. Its diameter is about 12,104 kilometres, or 7,521 miles, about 95% of Earth's diameter. Its mass is about 82% of Earth's mass. Its average density is similar, suggesting a similar internal structure with an iron core, a rocky mantle, and a thin crust. Venus orbits at about 108 million kilometres from the Sun, about 72% of Earth's orbital distance. It receives about twice as much solar radiation as Earth, but that alone wouldn't explain its extreme conditions. The key to Venus's hellish climate is its atmosphere. Venus has the thickest atmosphere of any terrestrial planet, a crushing blanket of gas that exerts a surface pressure about 92 times greater than Earth's atmosphere at sea level. Standing on Venus's surface would feel like being a kilometre underwater on Earth. The weight of all that overlying air is enough to crush most Earth machinery, and indeed, every lander we've sent to Venus has been crushed and stopped working within an hour or two. But the pressure is only part of the problem. Venus's atmosphere is about 96% carbon dioxide, with clouds of sulfuric acid droplets floating in the upper atmosphere. The carbon dioxide acts as an extraordinarily efficient greenhouse gas, trapping heat and raising surface temperatures to about 470 degrees Celsius, or 875 degrees Fahrenheit. This is hot enough to melt lead, zinc, and tin. It's hotter than Mercury's daytime temperature, despite Venus being almost twice as far from the Sun. Venus is the hottest planet in the solar system, and it's hot everywhere, at the equator and the poles, day and night, all the time. The thick atmosphere transports heat so efficiently that there's essentially no temperature variation across the surface. The greenhouse effect on Venus is so extreme that it's often cited as a worst-case scenario for climate change on Earth. Venus probably didn't start out this way. Early in its history, Venus might have had liquid water oceans and a more temperate climate. But Venus's proximity to the Sun meant more solar radiation, which evaporated water into the atmosphere. Water vapour is itself a greenhouse gas, and the increased water vapour trapped more heat, which evaporated more water, which trapped more heat, in a runaway greenhouse effect. Eventually, all of Venus's water was in the atmosphere. The intense ultraviolet radiation from the Sun broke apart water molecules, separating hydrogen and oxygen. The light hydrogen escaped into space, lost forever, while the oxygen combined with carbon from volcanic outgassing and other sources, forming more carbon dioxide. Over hundreds of millions of years, Venus lost its water and gained a thick carbon dioxide atmosphere. Without water to weather rocks and lock carbon dioxide away in carbonates, the carbon dioxide accumulated unchecked, thickening the atmosphere and increasing the greenhouse effect until Venus reached its current state. Venus's surface is hidden beneath these thick clouds, invisible to optical telescopes. For centuries, Venus was a mystery world. Not until the 1960s, when radar could penetrate the clouds, did we begin to see the surface. Soviet Venera landers provided the first direct images in the 1970s and 80s, showing a rocky, flat landscape illuminated by the dull orange glow of sunlight filtering through the clouds. The images were eerie, showing a world that looked vaguely Earth-like in composition but utterly alien in atmosphere and temperature. Radar mapping from orbit, particularly by NASA's Magellan spacecraft in the early 1990s, revealed Venus's surface in detail. Venus has highlands and lowlands, mountains and plains, but the topography is more subdued than Earth's. About 80% of the surface consists of relatively flat volcanic plains, covered by lava flows. There are two major highland regions, Ishtar Terra in the north and Aphrodite Terra near the equator, roughly analogous to Earth's continents. Venus's highest mountain, Maxwell Montes in Ishtar Terra, reaches about 11 kilometres above the average surface level, higher than Mount Everest above sea level. But Venus has no plate tectonics like Earth does. There are no subduction zones, no mid-ocean ridges, no continents drifting around. Instead, Venus's crust appears to be a single, solid shell. Heat from the interior is released primarily through volcanism, and Venus may be more volcanically active than any other planet except Earth and Jupiter's moon Io. Large shield volcanoes dot the surface, some hundreds of kilometres across. There are also peculiar features called coronae, circular or oval structures surrounded by concentric ridges and troughs, thought to form where hot mantle plumes rise beneath the crust, bulging it upward and then subsiding. Impact craters are relatively scarce on Venus, and those that exist appear to be relatively young, suggesting that much of the surface was resurfaced by volcanic activity about 300 to 500 million years ago. Venus's rotation is bizarre. It rotates on its axis once every 243 Earth days, and it rotates retrograde, in the opposite direction from most other planets. If you could somehow stand on Venus's surface and watch the sky, you would see the sun rise in the west and set in the east about 117 Earth days later. A day on Venus, from sunrise to sunrise, lasts 117 Earth days, longer than a Venusian year of 225 Earth days. Why Venus rotates backward is not entirely clear. The most likely explanation involves gravitational interactions with the Sun and atmospheric tides. Venus's thick atmosphere, heated by the Sun, experiences strong tidal forces, and over billions of years, these tides may have gradually slowed Venus's original prograde rotation, brought it to a stop, and then spun it up again in the retrograde direction. Alternatively, a massive impact early in Venus's history might have knocked it into a retrograde spin, though this seems less likely given that Venus has no large moons that might have formed from such an impact. Venus has no moons at all, and it has no significant magnetic field. Without plate tectonics to keep the interior convecting efficiently, Venus's iron core may have cooled and solidified, shutting down any dynamo that might once have generated a magnetic field. Or perhaps the slow rotation rate means the core, even if partially molten, doesn't generate enough dynamo action to produce a field. In any case, Venus is unprotected from the solar wind, which slams directly into the upper atmosphere, stripping away particles and gradually eroding the atmosphere, though the atmosphere is so thick that this erosion is negligible on human timescales. The upper atmosphere of Venus is a dynamic place. The surface winds are weak, just a few kilometers per hour, but high in the atmosphere. At the cloud tops about 50 to 70 kilometers above the surface, powerful winds blow at speeds of about 100 meters per second, over 360 kilometers per hour. These winds circle the planet in just 4 to 5 Earth days, much faster than the planet itself rotates. This phenomenon, called superrotation, is not fully understood, but it's thought to result from a combination of solar heating and atmospheric dynamics. The clouds of Venus are made of sulfuric acid droplets, created when sulfur dioxide from volcanic eruptions reacts with water vapour in the atmosphere. These clouds are highly reflective, which is why Venus is so bright in our sky. The clouds completely enshroud the planet, never clearing, making Venus's albedo, its reflectivity, the highest of any major solar system body. About 75% of the sunlight hitting Venus is reflected back into space. Despite this, Venus is still incredibly hot because the 25% that does penetrate is trapped by the greenhouse effect. Venus has been visited by more spacecraft than any other planet except Mars, mostly Soviet Venera and Vega probes and American Pioneer and Magellan missions. These missions revealed a world of extremes, a world where the environment is so hostile that engineering a lander to survive is an extraordinary challenge. The heat and pressure destroy electronics, corrode metals, and deform structures. Yet these missions succeeded in returning data, images, and even soil samples from the surface, showing us a world that is at once tantalizingly Earth-like in its rocky composition and utterly alien in its atmospheric and surface conditions. Venus is a reminder of planetary diversity. Two worlds, similar in size and composition, orbiting the same star, ended up on radically different paths. Earth got oceans, a moderate climate, plate tectonics, a magnetic field, and eventually life. Venus got a runaway greenhouse, crushing pressure, sulfuric acid clouds, and a surface hot enough to glow. The difference came down to a few factors: distance from the sun, water content, volcanic outgassing rates, atmospheric chemistry. Small differences compounded over billions of years, and two twins became opposites. Understanding Venus helps us understand Earth. It helps us appreciate how fortunate we are that Earth found a stable, habitable climate, and it reminds us how delicate that balance might be. Venus is often called Earth's twin, but perhaps it's more accurate to call it Earth's evil twin, a cautionary example of what can happen when a planetary climate spirals out of control. Venus is beautiful from a distance, but up close it's a hell world, and there's something both terrifying and humbling about that contrast. Home. The only place in the universe where we know for certain that life exists. A world of blue oceans and green forests, of white clouds and ice caps, of bustling cities and quiet wilderness. Earth, the third rock from the sun, our oasis in the cosmic desert, the only place we can truly call home. Earth is a terrestrial planet, about 12,742 kilometers in diameter, the largest of the rocky planets in the inner solar system. Its mass is about 6 times 10 to the power of 24 kilograms, and its average density of 5.5 grams per cubic centimetre suggests a differentiated interior with a dense iron-nickel core surrounded by a rocky mantle and a thin crust. Earth orbits the Sun at an average distance of about 150 million kilometres, or 93 million miles, one astronomical unit by definition. This distance places Earth squarely in the habitable zone, sometimes called the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. Earth is in the sweet spot. But distance from the Sun is only part of the story. Earth's atmosphere, its protective blanket of gases, plays a crucial role in making the planet habitable. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and about 1% argon, water vapour, carbon dioxide, and trace gases. This mix is unusual. Most planetary atmospheres are dominated by carbon dioxide or hydrogen, but Earth's has been transformed over billions of years by biological and geological processes. The oxygen in Earth's atmosphere is particularly significant. Oxygen is highly reactive and doesn't accumulate in atmospheres on its own. Earth's oxygen comes almost entirely from photosynthesis, the process by which plants, algae, and photosynthetic bacteria convert sunlight, water, and carbon dioxide into sugars and oxygen. For the first 2 billion years of Earth's history, there was little free oxygen in the atmosphere. Then, about 2.5 billion years ago, photosynthetic organisms became abundant enough that they began pumping oxygen into the atmosphere faster than geological processes could remove it. The Great Oxidation Event, as it's called, fundamentally changed Earth's chemistry and climate, and paved the way for the evolution of complex oxygen-breathing life. Earth's atmosphere does more than just provide oxygen to breathe. It shields the surface from harmful ultraviolet radiation, burns up most meteoroids before they reach the ground, and creates the weather systems that distribute heat and water around the planet. The atmospheric greenhouse effect, kept in check by the carbon cycle and biological processes, maintains Earth's average surface temperature at about 15 degrees Celsius, or 59 degrees Fahrenheit, warm enough for liquid water oceans but cool enough for ice caps at the poles. Water is central to Earth's story. About 71% of Earth's surface is covered by liquid water oceans, and water exists in all 3 phases: ice in the polar caps and glaciers, liquid in the oceans, rivers and lakes, and vapour in the atmosphere. Earth is the only known world where liquid water is stable and abundant on the surface. This water, along with the chemical ingredients and energy sources present on early Earth, provided the conditions for life to emerge. Life on Earth appears to have arisen relatively quickly, at least in geological terms. The oldest confirmed fossils are about 3.5 billion years old, just 1 billion years after Earth's formation. These early life forms were simple, single-celled organisms, prokaryotes similar to modern bacteria. For the next 2 billion years, life remained single-celled, but it was already exerting a profound influence on the planet, producing oxygen, altering the chemistry of the oceans, and creating the first stromatolites, layered structures built by communities of microorganisms. About 1.5 billion years ago, more complex cells, eukaryotes, emerged. These cells had internal structures like nuclei and mitochondria, and they could be much larger and more complex than prokaryotes. The emergence of eukaryotes set the stage for the later evolution of multicellular life, and by about 600 million years ago, complex multicellular organisms, animals, plants and fungi, had appeared and began to diversify rapidly in what's called the Cambrian explosion. Since then, life on Earth has evolved into an astonishing variety of forms, from microscopic bacteria to towering redwood trees, from tiny insects to massive blue whales. Life has colonized nearly every available niche, from the deepest ocean trenches to the highest mountain peaks, from volcanic hot springs to Antarctic ice sheets. Earth's biosphere, the sum total of all living organisms and their environments, is a complex, interconnected system that has co-evolved with the planet's geology and atmosphere over billions of years. Earth's interior is dynamic. The planet's iron-nickel core, about 3,400 kilometers in radius, is divided into a solid inner core and a liquid outer core. The outer core's motion, driven by heat escaping from the interior and by the planet's rotation, generates Earth's magnetic field through a dynamo process. This magnetic field, extending tens of thousands of kilometers into space, deflects the solar wind and protects the atmosphere from being stripped away. Without the magnetic field, Earth might have suffered the same fate as Mars, losing much of its atmosphere and water over time. Above the core is the mantle, a thick layer of rock about 2,900 kilometers deep. The mantle is solid, but it can flow very slowly over geological timescales, creeping like thick molasses. Heat from the core and from radioactive decay in the mantle drives convection currents that slowly stir the rock. These currents rise in some places and sink in others, and where they reach the surface, they drive the motion of Earth's tectonic plates. Earth's crust, the thin outermost layer, is broken into about a dozen major tectonic plates and several smaller ones. These plates float on the partially molten upper mantle, moving at rates of a few centimeters per year, about as fast as fingernails grow. Where plates collide, mountains are pushed up and subduction zones form where one plate slides beneath another. Where plates pull apart, new crust is created at mid-ocean ridges. Where plates slide past each other, earthquakes shake the ground. Plate tectonics is the engine that shapes Earth's surface, creating continents, ocean basins, mountain ranges and island chains. Plate tectonics also plays a crucial role in regulating Earth's climate. When carbon dioxide dissolves in rainwater, it forms a weak acid that weathers rocks, locking carbon into minerals like calcium carbonate. These minerals wash into the oceans, where marine organisms use them to build shells and skeletons. When these organisms die, their remains settle on the ocean floor, eventually being subducted into the mantle at plate boundaries. The carbon is released back into the atmosphere through volcanic eruptions, completing the carbon cycle. This cycle acts as a thermostat, regulating atmospheric carbon dioxide levels and keeping Earth's climate stable over hundreds of millions of years. Earth has one large natural satellite, the Moon, about 3,474 kilometers in diameter, a bit more than a quarter of Earth's diameter. The Moon orbits at an average distance of about 384,000 kilometers, close enough that it's the second brightest object in our sky after the Sun, and exerts significant gravitational influence on Earth. The Moon's gravity creates tides in Earth's oceans, and over billions of years tidal friction has gradually slowed Earth's rotation and pushed the Moon farther away. Early in Earth's history, days were much shorter, perhaps only 10 hours long, and the Moon was much closer. The Moon is thought to have formed from debris created when a Mars-sized object collided with proto-Earth about 50 million years after the solar system's formation. This giant impact hypothesis explains the Moon's unusual composition, which is similar to Earth's mantle but depleted in iron and volatile elements. The collision vaporized the impactor and part of Earth's crust and mantle, and the debris quickly coalesced to form the Moon. Earth's orbit around the Sun is nearly circular, with an eccentricity of only about 0.017. The Earth-Sun distance varies by only about 3% over the course of a year. Earth's axis is tilted about 23.5 degrees relative to its orbital plane, and this axial tilt is responsible for the seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer, with longer days and more direct sunlight. 6 months later, when it's tilted away, it experiences winter. The southern hemisphere experiences opposite seasons. Earth's rotation rate is slowing very gradually due to tidal friction with the Moon, lengthening the day by about 1.7 milliseconds per century. At this rate, in a few hundred million years, a day will be 25 hours long. Over billions of years, Earth's rotation will slow enough that it becomes tidally locked to the Moon, always keeping the same face toward it, just as the Moon already keeps the same face toward Earth. But this will take so long that the Sun will likely have entered its red giant phase and consumed Earth before tidal locking is achieved. Earth is the most studied object in the solar system, for obvious reasons. We've mapped every inch of the surface, measured the atmosphere in exquisite detail, probed the interior with seismology, and catalogued millions of species of life. We've sent thousands of satellites into orbit to study weather, climate, geology, oceanography, and more. We've drilled kilometres into the crust, collected samples of rocks, ice, and water from around the world, and pieced together Earth's 4.5 billion year history. Yet for all we've learned, there's still so much we don't understand. How exactly did life begin? What mechanisms drive long-term climate change? How does the biosphere interact with the atmosphere and hydrosphere in ways we haven't yet recognised? What's the future of Earth's climate in an era of human-driven change? Earth is our laboratory, our classroom, and our home, and understanding it is not just an academic exercise. It's essential for our survival. When astronauts first photographed Earth from space, they were struck by its beauty and fragility. Earth, seen from the moon or from deep space, is a small, blue marble suspended in the blackness, wrapped in swirls of white clouds, the only splash of colour in a vast dark ocean of space. That image, the pale blue dot as Carl Sagan called it, is a reminder of how precious Earth is, how unique, and how important it is that we take care of it. In all the cosmos, as far as we know, there is no other place like Earth. It is, quite literally, the world. Mars, the fourth planet from the Sun, has captivated human imagination for millennia. Named after the Roman god of war for its blood-red colour in the night sky, Mars has been the subject of countless stories, myths, and scientific investigations. It's the most Earth-like planet in the solar system, yet profoundly different in ways both subtle and dramatic. Mars is a world of ancient river valleys and extinct volcanoes, of polar ice caps and global dust storms, a world that once might have been habitable and might, just might, still harbour microbial life in protected niches below the surface. Mars is smaller than Earth, about half the diameter and roughly 1/9 the mass. Its diameter is about 6,792 kilometres, or 4,220 miles. Despite being smaller, Mars has almost the same amount of dry land as Earth, because Earth's surface is mostly covered by oceans, whereas Mars's surface is entirely land. If you could somehow transport all of Earth's continents to Mars, they would cover the surface almost completely. Mars orbits the Sun at an average distance of about 228 million kilometres, or 142 million miles, about 1.5 times Earth's orbital distance. This places Mars just outside the inner edge of the habitable zone, but not so far that liquid water is impossible. Mars receives about 43% as much sunlight as Earth, and combined with its thin atmosphere, this results in a much colder climate. Average surface temperatures on Mars are about -63 degrees Celsius, or -81 degrees Fahrenheit, though daytime equatorial temperatures can climb above freezing during summer, while nighttime polar temperatures in winter can plunge below -125 degrees Celsius. Mars's atmosphere is thin, only about 1% as dense as Earth's atmosphere at sea level. It's composed mostly of carbon dioxide, about 95%, with small amounts of nitrogen and argon, and traces of oxygen, water vapour and other gases. The atmospheric pressure at the surface averages about 600 pascals, compared to Earth's 100,000 pascals. This low pressure means liquid water cannot exist on Mars's surface. Any exposed water ice would sublimate directly into vapour, and any liquid water would quickly boil away even at temperatures below 0 degrees Celsius. Yet Mars was not always this way. The surface is covered with features that unmistakably indicate flowing water in the past. There are ancient valley networks that look like dried riverbeds, carved by water flowing downhill billions of years ago. There are outflow channels, enormous channels carved by catastrophic floods that released volumes of water comparable to all the water in the Mediterranean Sea. There are lake beds, deltas where rivers once emptied into lakes or seas, and layers of sedimentary rock that suggest water-deposited minerals in ancient lake beds. All this evidence points to a warmer, wetter Mars in the distant past, perhaps 3.5 to 4 billion years ago. Back then, Mars may have had a thicker atmosphere, perhaps enough to greenhouse the surface above the freezing point of water, allowing rain to fall and rivers to flow. Lakes and perhaps even an ocean may have existed in the northern lowlands. This ancient Mars would have been more Earth-like, though probably still colder and drier than Earth is today. But Mars lost most of its atmosphere. The exact mechanism is still being studied, but it seems that Mars's small size and weak gravity made it easier for atmospheric particles to escape into space. Solar wind, which bombards Mars directly, because the planet has no global magnetic field to deflect it, stripped away atmospheric particles over billions of years. Mars's core, smaller than Earth's and cooling faster, may have solidified relatively early, shutting down any magnetic field the planet once had. Without the protection of a magnetic field, the atmosphere was vulnerable, and over time Mars transitioned from a world with rivers and lakes to the cold, dry, barren desert we see today. Mars is famous for its rust-red colour, caused by iron oxide, literally rust, in the surface rocks and dust. The Martian soil is rich in iron minerals that have been oxidized, reacted with oxygen, to form the red iron oxide that coats everything. This gives Mars its distinctive hue, visible even from Earth with the naked eye. But the surface is not uniformly red. There are dark basaltic rocks, lighter coloured dust, and bright polar ice caps of water ice and carbon dioxide ice. Mars's surface is divided into two distinct regions. The southern hemisphere is heavily cratered, ancient highlands, dating back billions of years to Mars's early history. The northern hemisphere is younger, smoother lowlands, perhaps resurfaced by volcanic or fluvial activity. The boundary between these two regions is sharp, a global escarpment several kilometres high, and the origin of this dichotomy is one of the great unsolved mysteries of Martian geology. Some scientists think a massive impact early in Mars's history excavated the northern lowlands. Others propose volcanic resurfacing or other internal processes. Mars has some of the most spectacular geological features in the solar system. Olympus Mons, the largest volcano in the solar system, rises about 22 kilometres above the surrounding plains, more than twice as high as Mount Everest above sea level, and its base is about 600 kilometres across. Olympus Mons is a shield volcano, similar in shape to the volcanoes of Hawaii, built up by layer upon layer of lava flows over hundreds of millions of years. It's currently dormant, but it may not be extinct. Mars has several other large volcanoes in the Tharsis region, and these volcanoes are evidence of a geologically active past. Near Tharsis is Valles Marineris, a vast canyon system stretching more than 4,000 kilometres along the Martian equator, about a quarter of the planet's circumference. It's up to 7 kilometres deep and 200 kilometres wide in places, dwarfing Earth's Grand Canyon. Valles Marineris is thought to have formed from tectonic activity associated with the Tharsis Bulge, a massive volcanic uplift that may have stretched and fractured the surrounding crust. Mars has two small moons, Phobos and Deimos, named after the twin sons of the god Mars in Greek mythology. Both are irregularly shaped, heavily cratered, and very small. Phobos is about 22 kilometres across at its longest, while Deimos is about 12 kilometres. They're so small that their gravity is insufficient to pull them into spherical shapes. They orbit close to Mars, Phobos at about 9,400 kilometres, and Deimos at about 23,000 kilometres. For comparison, Earth's moon orbits at about 384,000 kilometres. Phobos and Deimos are likely captured asteroids, objects that formed in the asteroid belt and were later captured by Mars's gravity. But their orbits are nearly circular and lie almost exactly in Mars's equatorial plane, which is unusual for captured objects, and has led some scientists to propose that they might have formed from debris ejected by a massive impact on Mars early in its history, similar to how Earth's moon formed. Phobos has an unusual fate. It orbits so close to Mars that tidal forces are gradually pulling it closer. In about 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces, creating a ring system around the planet. Deimos, farther out, is slowly drifting away from Mars and will eventually escape into space. Mars has been the target of more spacecraft missions than any planet except Earth. From the first flybys in the 1960s to the orbiters, landers and rovers operating today, humanity has studied Mars intensively. The Viking landers in the 1970s, the Mars Pathfinder and its Sojourner rover in 1997, the Twin Spirit and Opportunity rovers in the 2000s, the Curiosity rover since 2012, and the Perseverance rover and Ingenuity helicopter since 2021 have all explored the Martian surface, analysing rocks, drilling into the soil, searching for signs of past or present life. These missions have revealed Mars to be a complex dynamic world, not the dead, static ball of dust that early telescopic observations might have suggested. Mars has weather, with clouds, dust storms and even snow. Global dust storms can occasionally envelop the entire planet, turning the sky dark for months. Seasonal changes are visible as carbon dioxide ice sublimates from one polar cap in spring and condenses on the other in autumn. Small whirlwinds called dust devils race across the surface, lifting dust and leaving trails behind them. Water ice is abundant just below the surface at high latitudes, and the polar caps contain enough water ice that, if melted, could cover the entire planet in a global ocean several meters deep. There's also evidence of liquid brines, very salty water, flowing seasonally on some slopes, though the interpretation of this evidence is still debated. The question of whether Mars currently harbours life, even just microbial life, remains unanswered. No definitive biosignatures have been found, but the search continues. Mars is the next frontier for human exploration. Multiple space agencies and private companies are planning missions to send humans to Mars within the next few decades. The challenges are immense. The journey takes months. The radiation exposure is significant, the low gravity could cause health problems, and the lack of a breathable atmosphere and surface water means astronauts would need to be entirely self-sufficient. But the scientific rewards and the symbolic achievement of setting foot on another planet make Mars an irresistible goal. Mars represents possibility. It's close, enough to reach with current technology, yet far enough to be a real challenge. It's similar enough to Earth that we can imagine living there, yet different enough to demand innovation and adaptation. It had liquid water in the past, raising the tantalizing possibility that life once existed there and might still exist in protected subsurface environments. Mars is a world waiting to be explored, and in the coming decades and centuries, it will likely become humanity's first true foothold beyond Earth. Between the orbits of Mars and Jupiter lies a region of the solar system that's often misunderstood. In movies and television, it's depicted as a dense field of tumbling rocks, a chaotic obstacle course that spaceships must navigate carefully to avoid collisions. In reality, the asteroid belt is mostly empty space, punctuated by millions of small rocky and metallic objects, most of them separated by distances of hundreds of thousands or even millions of kilometers. You could fly a spacecraft through the asteroid belt and your chances of randomly hitting an asteroid would be vanishingly small. The asteroid belt contains a vast number of objects, from boulder-sized fragments to the dwarf planet Ceres, which is about 940 kilometers in diameter. Current estimates suggest there are about 1 to 2 million asteroids larger than 1 kilometer and many millions more smaller objects. But even with all these objects, the total mass of the asteroid belt is only about 4% of the Moon's mass, or about 1/2000th of Earth's mass. The asteroids are spread out over an enormous volume of space, from about 2 to 3.5 astronomical units from the Sun, and they occupy a three-dimensional volume, not just a flat plane. Asteroids are remnants from the solar system's formation, planetesimals that never accumulated into a planet. In the early solar system, this region probably contained much more material, perhaps enough to form a planet as large as Earth or Mars. but the gravitational influence of nearby Jupiter, the solar system's most massive planet, stirred up the asteroid belt, increasing collision velocities. Instead of gentle impacts that allowed objects to merge, collisions became violent and fragmenting. Objects were shattered rather than accumulated, and many were ejected from the belt entirely, flung into the Sun or out of the solar system, or perturbed into planet-crossing orbits. Over billions of years, the asteroid belt has been slowly depleting as asteroids are lost to collisions, ejections, and spiral into the Sun due to various effects like radiation pressure and gravitational interactions. The belt we see today is just a remnant of what was once there. Asteroids come in different types based on their composition. C-type or carbonaceous asteroids are the most common, making up about 75% of known asteroids. They're dark with low albedos, meaning they reflect very little sunlight, and they're rich in carbon compounds. They're thought to be primitive, relatively unchanged since the solar system's formation, and they're found mainly in the outer parts of the asteroid belt where temperatures were low enough for volatile compounds to condense. S-type or silicaceous asteroids make up about 17% of known asteroids. They're brighter, more reflective, and composed mainly of silicate minerals and some metal. They dominate the inner asteroid belt. M-type asteroids, metallic asteroids made mostly of iron and nickel, are much less common but extremely interesting. They may be the exposed cores of differentiated planetesimals that were shattered by collisions, revealing their metallic interiors. The largest object in the asteroid belt is Ceres, classified as a dwarf planet since 2006. Ceres is massive enough that its gravity has pulled it into a roughly spherical shape, and it has a differentiated interior with a rocky core surrounded by a mantle of water ice and possibly a subsurface ocean. Observations from NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a world with bright spots in some craters, likely deposits of salts left behind when briny water sublimated, and evidence of recent geological activity, including possible cryovolcanoes that erupt water and salts instead of molten rock. Other large asteroids include Vesta, Pallas, and Hygiea, all several hundred kilometers in diameter. Vesta is particularly interesting because it's differentiated, with a metal core, rocky mantle, and basaltic crust, making it more like a small planet than a primitive asteroid. The Dawn spacecraft also orbited Vesta, and found it to have a huge impact basin near its south pole, so large that it created a family of smaller asteroids from the ejected debris. Some meteorites found on Earth, the head meteorites, are thought to be fragments of Vesta's crust blasted into space by impacts. The asteroid belt is not uniformly distributed. There are regions called Kirkwood gaps where asteroids are scarce, caused by orbital resonances with Jupiter. For example, an asteroid orbiting at a distance where it completes exactly 3 orbits for every one of Jupiter's would be in a 3-to-1 resonance. Every third orbit, the asteroid would be in the same position relative to Jupiter, receiving a gravitational tug that, over millions of years, would add up and perturb the asteroid's orbit, either pushing it inward or outward until it's no longer in resonance. These gaps are like grooves carved in the distribution of asteroids by Jupiter's gravitational influence. Some asteroids have orbits that take them out of the belt and into the inner solar system, where they can cross the orbits of the terrestrial planets. These are called near-Earth asteroids, and they're of particular interest because they pose a potential impact hazard to Earth. Collisions with large asteroids are rare on human timescales, but have happened many times in Earth's history, sometimes with catastrophic consequences. The Chicxulub impact 66 million years ago, caused by an asteroid about 10 kilometers in diameter, led to the extinction of the dinosaurs and about 75% of all species on Earth. Today, astronomers monitor near-Earth asteroids, cataloguing their orbits and assessing potential future impacts. NASA and other space agencies have missions planned to test methods of deflecting asteroids, changing their orbits slightly so they miss Earth. The threat is real but manageable with sufficient warning and preparation. Asteroids are also scientifically valuable. They're time capsules, preserving material from the solar system's youth. Studying them helps us understand what the protoplanetary disk was like, how planets formed, and how the solar system evolved. Several spacecraft missions have visited asteroids, taking samples and returning them to Earth for detailed analysis. The Japanese Hayabusa and Hayabusa 2 missions returned samples from asteroids Itokawa and Ryugu, while NASA's OSIRIS-REx mission returned samples from asteroid Bennu. These samples contain organic molecules, water and minerals that provide clues about the building blocks of planets and possibly the origin of life. In the future, asteroids might also be economically valuable. Many contain metals like iron, nickel, platinum, and rare earth elements that are valuable on Earth. The idea of asteroid mining, sending robotic missions to extract these materials and bring them back to Earth, or use them in space, is still in the realm of science fiction, but it's being seriously studied. Some asteroids contain more metal than has been mined in all of human history. The logistical and economic challenges are enormous, but the potential rewards are equally large. The asteroid belt is a frontier, a region of the solar system that's largely unexplored but full of potential. It's a graveyard of failed planetary formation, but it's also a museum of the solar system's past, and possibly a resource trove for the future. As we continue to explore the belt with telescopes and spacecraft, we'll learn more about these ancient enigmatic objects and the role they've played in shaping the solar system we know today. If the Sun is the monarch of the solar system, Jupiter is its crown prince, a world so massive, so dominant, that it has shaped the entire solar system's structure and evolution. Jupiter is not just the largest planet. It's more massive than all the other planets, moons, asteroids and comets combined. If you could somehow gather up every object in the solar system except the Sun and pile them together, Jupiter would still be more than twice as massive as everything else put together. Jupiter is, in many ways, a planetary system unto itself, a miniature solar system with dozens of moons, a thin ring system, and complex atmospheric dynamics. Jupiter is a gas giant, fundamentally, different from the terrestrial planets. It has no solid surface. If you could somehow descend through Jupiter's atmosphere, you would find the gas getting denser and denser, hotter and hotter, until eventually the pressure is so great that hydrogen, which makes up most of Jupiter's mass, is compressed into a metallic liquid state. You'd never hit a solid surface. You'd simply be crushed and vaporized by the pressure and temperature long before reaching the core, which is probably a solid ball of rock and ice, but buried under tens of thousands of kilometers of supercritical fluid. Jupiter's equatorial diameter is about 143,000 kilometers, or 89,000 miles, more than 11 times Earth's diameter. Its volume is so large you could fit about 1,300 Earths inside it. Yet despite this enormous size, Jupiter's mass is only 318 times Earth's mass, which means Jupiter's average density is quite low, about 1.3 grams per cubic centimetre, only a little more than water. This low density confirms that Jupiter is made mostly of light elements, hydrogen and helium, the same elements that dominate the Sun. Jupiter orbits the Sun at an average distance of about 778 million kilometres, or 484 million miles, about 5.2 astronomical units. At this distance, Jupiter receives only about 4% as much sunlight per unit area as Earth does, and the temperature in the upper atmosphere is cold, around negative 145 degrees Celsius. But Jupiter radiates more energy into space than it receives from the Sun. The planet is still slowly contracting from its formation, and this contraction releases gravitational potential energy as heat. This internal heat drives Jupiter's weather systems and contributes to the incredibly fast winds and long-lived storms that characterize the planet's atmosphere. Jupiter's atmosphere is divided into distinct bands parallel to the equator, alternating light zones and dark belts. The zones are regions of rising gas, cooler and higher altitude, where ammonia ice condenses into bright clouds. The belts are regions of sinking gas, warmer and lower altitude, where clouds are thinner and we're seeing deeper, darker layers. The boundaries between zones and belts are jet streams, powerful winds that can reach speeds of over 500 kilometers per hour. These jet streams are far faster and more stable than Earth's jet streams. Earth's weather is dominated by complex interactions between land, ocean and atmosphere, and our jet streams meander and shift constantly. Jupiter has no solid surface and no oceans, so the atmospheric dynamics are simpler in some ways, driven primarily by internal heat and rotation. Jupiter rotates incredibly fast for such a large object. A day on Jupiter, the time it takes to rotate once on its axis, is only about 10 hours. This rapid rotation creates strong, Coriolis forces that organise the atmospheric flow into these parallel bands. Embedded in the cloud bands are storms, swirling vortices of various sizes. The largest and most famous is the Great Red Spot, a storm larger than Earth that has been continuously observed for at least 350 years, though it may be even older. The Great Red Spot is an anticyclone, a high-pressure storm rotating counterclockwise in Jupiter's southern hemisphere. It's a persistent feature, unlike any storm on Earth, which typically lasts days or weeks at most. The Great Red Spot's longevity is partly due to Jupiter's lack of a solid surface. On Earth, hurricanes lose energy when they pass over land, but Jupiter's storms have no land to run into. They can persist indefinitely as long as they're fed by energy from below and aren't disrupted by other storms. The Great Red Spot has been shrinking for decades, and it's now about half the size it was a century ago, but it shows no signs of disappearing entirely anytime soon. The colour of the Great Red Spot, and of Jupiter's clouds in general, comes from complex organic compounds, created by the action of ultraviolet light and cosmic rays on simple molecules like ammonia and methane. The exact chemistry is still being studied, but it seems that sulfur and phosphorus compounds play a role in creating the reds, browns and yellows that tint the clouds. High-altitude ammonia ice clouds are white, but below them are layers of ammonium hydrosulfide and water ice clouds, and these different layers, along with the organic compounds, create the variegated palette we see. Jupiter's composition is about 76% hydrogen and 24% helium by mass, with traces of methane, ammonia, water vapour and other compounds. This composition is very similar to the Sun's and to the primordial composition of the solar nebula. Jupiter, being so massive, was able to gravitationally capture and retain the lightest elements, whereas smaller planets could not. In a sense, Jupiter is a failed star. If it had been about 80 times more massive, the pressure and temperature in its core would have been high enough to ignite hydrogen fusion, and Jupiter would have become a star. But it didn't reach that threshold, so it remains a planet, albeit a very large and impressive one. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's field. This field is generated by a dynamo effect in the metallic hydrogen layer deep in Jupiter's interior. The magnetic field extends far into space, forming a magnetosphere that dwarfs the planet itself. Jupiter's magnetosphere extends outward for several million kilometers in some directions, and if you could see it from Earth, it would appear larger than the full moon in the sky, despite Jupiter being so much farther away. The magnetosphere traps charged particles from the solar wind and from volcanic eruptions on Jupiter's moon, Io. These particles are accelerated to high speeds by the magnetic field, creating intense radiation belts around Jupiter. The radiation near Jupiter is so intense that it's a major concern for spacecraft exploring the system. Several robotic missions have had to be carefully designed to survive the radiation environment, using radiation-hardened electronics and shielding. Jupiter has at least 95 known moons, and more are being discovered regularly as surveys improve. Most of these moons are small, irregular objects, probably captured asteroids or comets. But 4 of Jupiter's moons are large and round, with complex geologies of their own. These are the Galilean moons, named after Galileo Galilei, who discovered them in 1610 using his newly invented telescope. Io, Europa, Ganymede, and Callisto. Io is the innermost Galilean moon and the most volcanically active body in the solar system. Tidal heating, caused by gravitational interactions between Io, Europa and Jupiter, continually flexes Io's interior, melting rock and driving hundreds of active volcanoes. Io's surface is coated with sulfur and sulfur dioxide from these volcanoes, giving it a yellow, orange and red appearance. There are no impact craters visible on Io because volcanic resurfacing erases them within a few million years. Europa is slightly smaller than Earth's moon and covered by a smooth shell of water ice. Beneath the ice is almost certainly a global ocean of liquid water, kept liquid by tidal heating. The ice shell is crisscrossed by cracks and ridges, and there's evidence that the ocean occasionally breaks through the ice in localized eruptions. Europa's ocean may contain twice as much water as all of Earth's oceans combined, and it's considered one of the most promising places in the solar system to search for extraterrestrial life. Ganymede is the largest moon in the solar system, even larger than the planet Mercury, and the only moon known to have its own magnetic field. Ganymede has an icy surface with both dark, ancient, cratered terrain and lighter groove terrain that appears to have been tectonically active relatively recently. Beneath the surface there's likely another subsurface ocean, though not as easily accessible as Europa's. Callisto is the outermost Galilean moon, and the most heavily cratered, suggesting an ancient surface that has remained largely unchanged for billions of years. Callisto seems to be less geologically active than the other Galilean moons, perhaps because it's far enough from Jupiter that tidal heating is minimal. Yet it too may have a subsurface ocean. Jupiter also has a faint ring system, discovered by the Voyager spacecraft in 1979. The rings are composed of tiny dust particles, probably blasted off Jupiter's small inner moons by micrometeorite impacts. The rings are far less prominent than Saturn's magnificent ring system, and are difficult to see except when backlit by the Sun. Jupiter has been visited by multiple spacecraft, including the Pioneer and Voyager missions in the 1970s and 80s, the Galileo orbiter from 1995 to 2003, and the Juno spacecraft, which has been orbiting Jupiter since 2016. These missions have revealed Jupiter to be far more complex and dynamic than telescopic observations alone could show, with deep atmospheric circulation, powerful gravity that affects the entire solar system, and a system of moons that are worlds unto themselves. Jupiter's gravitational influence extends throughout the solar system. It's thought to have played a crucial role in the solar system's early evolution, migrating inward toward the Sun and then back outward, clearing out much of the asteroid belt and flinging countless planetesimals into the outer solar system or into interstellar space. Jupiter's gravity continues to deflect comets and asteroids today, acting as a shield that protects the inner planets from some impacts. Without Jupiter, Earth would likely have been struck by far more large asteroids over its history, possibly preventing the stable climate and long timescales that allowed complex life to evolve. Jupiter is a reminder of the diversity of worlds in the solar system. It's a planet ruled by fluid dynamics and magnetic fields rather than solid geology. A world where weather systems can persist for centuries and moons can harbour oceans beneath icy crusts. Jupiter is the king of planets, vast, powerful, and endlessly fascinating. If Jupiter is the king of planets, Saturn is surely the most beautiful. With its stunning system of rings catching and reflecting sunlight, Saturn is the jewel of the solar system, an object so visually striking that even a casual glance through a small telescope leaves an indelible impression. But Saturn is far more than just pretty rings. It's a world of powerful winds, a rich retinue of moons including one with a thick atmosphere and liquid lakes, and a complex magnetosphere. Saturn is a gas giant like Jupiter, but with its own unique characteristics and mysteries. Saturn is the second largest planet, with an equatorial diameter of about 120,000 kilometres, or 75,000 miles. It's smaller than Jupiter, but still about 9.5 times wider than Earth. Saturn's mass is about 95 times Earth's mass, less than a third of Jupiter's, which makes Saturn the least dense of all the major planets. Saturn's average density is only about 0.69 grams per cubic centimetre, less than water. If you could find a bathtub large enough, Saturn would float. This low density reflects Saturn's composition, which, like Jupiter, is dominated by hydrogen and helium. About 96% of Saturn's mass is hydrogen, with helium making up most of the rest and traces of other elements like methane, ammonia, and water vapour. Saturn's interior structure is probably similar to Jupiter's, with a small rocky and icy core surrounded by layers of metallic hydrogen, liquid molecular hydrogen, and a gaseous atmosphere, but the exact boundaries between these layers are uncertain. Saturn orbits the Sun at an average distance of about 1.43 billion kilometres, or 886 million miles, about 9.5 astronomical units. This places it far from the Sun, receiving only about 1% as much sunlight per unit area as Earth does. Temperatures in the upper atmosphere are around negative 140 degrees Celsius, cold enough that ammonia and water vapour condense into clouds. Like Jupiter, Saturn radiates more energy into space than it absorbs from the Sun, the excess coming from residual heat left over from the planet's formation, and from helium rain deep in the interior, where helium precipitates out of solution in the metallic hydrogen and falls toward the core, converting gravitational potential energy into heat. Saturn rotates rapidly, once every 10 hours and 33 minutes at the equator, creating strong Coriolis forces that organise the atmosphere into banded jet streams similar to Jupiter's. But Saturn's atmospheric bands are less pronounced and more muted in colour, probably because a high-altitude haze of ammonia ice obscures the deeper cloud layers. The winds on Saturn are the fastest in the solar system, reaching speeds of up to 1,800 km per hour, or 1,100 miles per hour at the equator. These winds blow predominantly eastward, in the same direction as the planet's rotation, and they're faster than any winds on Jupiter. Saturn's atmosphere hosts occasional large storms that can encircle the planet. These great white spots appear about once every 30 years, during Saturn's northern hemisphere spring and summer, and they can grow to cover areas larger than Earth. The storms are thought to be triggered by seasonal heating, which causes instabilities in the atmosphere that erupt as massive storm systems. The most recent great white spot was observed in 2010 to 2011 and lasted for about 7 months before dissipating. At Saturn's north pole, there's a remarkable atmospheric feature that's entirely unique in the solar system, a persistent hexagonal jet stream. The hexagon is enormous, about 30,000 kilometres across, larger than Earth, and its 6 sides are clearly defined edges of a powerful jet stream that rotates around the pole every 10.5 hours, the same as the planet's rotation period. The hexagon has been continuously observed since the Voyager spacecraft first imaged it in the early 1980s, and it's still there today, showing that it's an extraordinarily stable feature. Scientists think the hexagonal shape is caused by wave patterns in the jet stream interacting with the planet's rotation, but the exact mechanism is still being studied. But Saturn's most famous feature is its ring system, the most extensive and spectacular in the solar system. While Jupiter, Uranus, and Neptune also have rings, and possibly some asteroids and centaurs do as well, none compare to Saturn's rings for sheer beauty and complexity. Saturn's rings extend from about 74,000 to 140,000 kilometres from the planet's centre, or about 12,000 to 120,000 kilometres above the cloud tops. They're remarkably thin, only about 10 to 100 metres thick on average, making them essentially a two-dimensional disk of particles. The rings are composed of countless particles ranging in size from tiny dust grains to house-sized chunks, but most are about the size of a snowball or a car. These particles are almost pure water ice, about 95% or more, with small amounts of rocky material and organic compounds. The ice makes the rings highly reflective, catching sunlight and creating the brilliant display we see. The rings are not solid structures but swarms of individual particles, each one orbiting Saturn independently according to Kepler's laws. Particles in the inner rings orbit faster than those in the outer rings, and collisions between particles are frequent but gentle, allowing the rings to spread out and maintain their structure. The rings are named with letters in the order they were discovered, not in the order of their position. The main rings, from innermost to outermost, are the D ring, the C ring, the B ring, which is the brightest and most massive, the Cassini division, which is a gap in the rings, the A ring, the F ring, and then several fainter outer rings. The structure within the rings is incredibly complex, with thousands of ringlets and gaps created by gravitational interactions with Saturn's moons. Some gaps are swept clear by small moons, called shepherd moons, that orbit within or near the rings and gravitationally shepherd the ring particles, preventing them from spreading into the gap. The F ring, for example, is shepherded by two small moons, Prometheus and Pandora, which keep the ring narrow and create kinks and braids in the ring structure. The origin of Saturn's rings is still debated. One possibility is that they're remnants from the formation of Saturn and its moons, material that never coalesced into a moon because it was too close to Saturn and subject to tidal forces that prevented accretion. Another possibility is that the rings are the debris from a moon, or moons that wandered too close to Saturn and were torn apart by tidal forces, or that were destroyed by a collision. Recent studies suggest the rings may be relatively young, perhaps only a few 100 million years old, and may eventually dissipate over the next 100 million years as particles spiral inward and rain onto Saturn's atmosphere or are lost to space. Saturn has at least 146 known moons, more than any other planet, though many of these are tiny, irregular, objects likely captured from the Kuiper Belt or asteroid belt. The largest and most interesting is Titan, the second largest moon in the solar system and the only moon with a thick atmosphere. Titan is about 5150 kilometers in diameter, larger than the planet Mercury, and it's massive enough that its gravity has pulled it into a spherical shape. Titan's atmosphere is about 1.5 times as dense as Earth's at sea level, and composed mostly of nitrogen, about 95%, with a few percent methane and traces of other hydrocarbons and organic compounds. The methane and hydrocarbons create a thick orange haze that completely obscures the surface in visible light, but infrared and radar observations have revealed a complex landscape beneath. Titan's surface has lakes and seas filled not with water, which is frozen solid at Titan's temperature of negative 180 degrees Celsius, but with liquid methane and ethane. These hydrocarbon lakes are found primarily in the polar regions, and the largest, Kraken Mare, covers about 400,000 square kilometres, larger than the Caspian Sea on Earth. Titan has a methane cycle analogous to Earth's water cycle, with methane evaporating from the lakes, forming clouds, and raining back onto the surface, carving channels and depositing sediments. Titan is thought to have a subsurface ocean of liquid water beneath its icy crust, kept liquid by tidal heating and radioactive decay in the interior. The combination of a thick atmosphere, organic chemistry, and possibly both surface and subsurface liquids makes Titan one of the most intriguing places in the solar system for the study of prebiotic chemistry and the potential for life. Another remarkable moon is Enceladus, a small icy moon about 500 kilometers in diameter. Enceladus was thought to be geologically dead until the Cassini spacecraft discovered geysers of water vapor, ice crystals, and organic compounds erupting from cracks near the South Pole. These plumes are evidence of a subsurface ocean beneath Enceladus's ice shell, and the material in the plumes suggests hydrothermal activity on the ocean floor, similar to the hydrothermal vents on Earth's ocean floors that support rich ecosystems. Enceladus's ocean is now considered another prime target in the search for extraterrestrial life. Saturn has been visited by several spacecraft, most notably the Cassini orbiter, which studied the Saturn system from 2004 to 2017. Cassini provided an unprecedented detailed look at Saturn's atmosphere, rings and moons, making numerous discoveries and transforming our understanding of this distant world. The mission ended when Cassini, running low on fuel, was deliberately plunged into Saturn's atmosphere to avoid contaminating potentially habitable moons like Enceladus or Titan with Earth microbes that might have hitchhiked on the spacecraft. Saturn is a world of superlatives, the most beautiful, the least dense, the one with the fastest winds and the most moons. Its rings are a cosmic work of art, its largest moon a place with an Earth-like methane cycle and perhaps prebiotic chemistry, and its small icy moons may harbour oceans beneath their frozen crusts. Saturn reminds us that the solar system is full of wonders, each world unique, each with its own story to tell. Uranus is the 7th planet from the Sun, and one of the least explored worlds in the solar system. It's so distant and faint that it was unknown to ancient astronomers, and was only discovered in 1781 by William Herschel, making it the first planet discovered with a telescope. Uranus is an ice giant, smaller and less massive than Jupiter and Saturn, but still far larger than any terrestrial planet. And Uranus has a unique characteristic that sets it apart from every other planet. It's tipped over on its side, spinning with its axis of rotation nearly in the plane of its orbit. Uranus has an equatorial diameter of about 50,724 kilometres, or 31,522 miles, about 4 times wider than Earth. Its mass is about 14.5 times Earth's mass, much less than Jupiter or Saturn, but still substantial. Despite this mass, Uranus is less dense than the gas giants, with an average density of about 1.27 grams per cubic centimetre, suggesting a different internal composition. Uranus is called an ice giant because its interior is thought to be composed mainly of water, methane and ammonia ices, along with rock, and possibly a small iron-nickel core. The term ice here doesn't necessarily mean frozen solid. Deep in Uranus's interior, where pressures are millions of times Earth's atmospheric pressure and temperatures are thousands of degrees, these compounds are in exotic high-pressure phases, perhaps liquid or supercritical fluids. The exact structure of Uranus's interior is uncertain because we have so little data, but models suggest a layered structure with a rocky core surrounded by an icy mantle, and a relatively thin atmosphere of hydrogen, helium, and methane. Uranus orbits the Sun at an average distance of about 2.87 billion kilometres, or 1.78 billion miles, about 19.2 astronomical units. At this distance, sunlight is dim, about 1/300th as bright as on Earth, and temperatures in the upper atmosphere are frigid, around negative 215 degrees Celsius, making Uranus the coldest planet in the solar system, even colder than Neptune despite being closer to the Sun. This cold temperature is puzzling because Uranus, unlike Jupiter, Saturn and Neptune, does not seem to radiate significantly more heat than it receives from the Sun. Some scientists think Uranus may have lost much of its internal heat early in its history, perhaps due to a giant impact that tipped the planet on its side. That axial tilt is Uranus's most distinctive feature. The planet's rotation axis is tilted about 97.77 degrees relative to its orbital plane, meaning Uranus essentially rolls around the Sun like a ball rather than spinning like a top. One pole points almost directly at the Sun for about 42 Earth years, during which that hemisphere experiences continuous summer, while the other hemisphere is in continuous winter. Then, after Uranus has moved halfway around its orbit, the roles reverse. The equatorial regions experience day and night cycles, but the polar regions experience decades-long seasons. This extreme tilt is thought to be the result of one or more giant impacts early in the planet's history. A collision with an Earth-sized or larger object could have knocked Uranus over, and if the impact occurred late in Uranus's formation, the planet wouldn't have had time to reorient itself before settling into its current configuration. Some models suggest multiple smaller impacts might also explain the tilt. Interestingly, Uranus's moons and rings all orbit in the planet's equatorial plane, meaning they too are tipped over, consistent with them forming after the impact that tipped the planet. Uranus's atmosphere is composed mostly of hydrogen and helium, about 83% and 15% by mass respectively, with about 2% methane and traces of other compounds. The methane in the upper atmosphere absorbs red light, giving Uranus a blue-green colour. Unlike Jupiter and Saturn, Uranus's atmosphere appears very bland in visible light, with few distinct features. For a long time, telescopic observations showed little more than a featureless blue-green disk. But more recent observations, especially from the Hubble Space Telescope and from large ground-based telescopes using adaptive optics, have revealed faint bands, clouds, and storm systems. One reason Uranus's atmosphere appears so bland may be the low internal heat. On Jupiter and Saturn, internal heat drives strong convection and vigorous atmospheric dynamics, creating the prominent bands and storms. Uranus, radiating little internal heat, has weaker atmospheric circulation and fewer conspicuous weather features. But there are occasional storms, bright clouds that appear and disappear, and seasonal changes as different hemispheres tilt toward the Sun. Uranus has a magnetic field, discovered by Voyager 2 during its flyby in 1986, but the field is unusual. It's tilted about 60 degrees relative to the planet's rotation axis, and offset from the planet's centre by about a third of Uranus's radius. This means the magnetic field is highly asymmetric, with the magnetic poles not aligned with the geographic poles. As Uranus rotates, the magnetic field wobbles dramatically, creating an extremely complex magnetosphere. The origin of this strange magnetic field is not well understood, but it may relate to the fact that the field is generated not in a central core but in a shell of conducting icy fluids at intermediate depths. Uranus has 13 known rings, all quite faint and composed of dark particles. The rings were discovered in 1977 when Uranus passed in front of a distant star and the rings briefly blocked the starlight. Observations from Earth and from Voyager 2 revealed a system of narrow, sharply defined rings separated by gaps. The rings are dark, reflecting only a few % of incident sunlight, and they're composed of small particles, probably water ice mixed with darker organic compounds that have been darkened by radiation. The rings may be relatively young, perhaps formed from the breakup of small moons. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are icy worlds, probably composed of roughly equal parts rock and water ice, and they show evidence of past geological activity. Miranda is the smallest and strangest of the large moons, with a surface that looks like a jumbled patchwork of different terrains. There are old, heavily cratered regions alongside younger, grooved terrains and cliffs that are among the tallest in the solar system. Miranda's appearance suggests it was geologically active in the past, possibly due to tidal heating from orbital resonances with other moons, but exactly what happened is still debated. Titania and Oberon, the largest Uranian moons, show evidence of past resurfacing and faulting, while Ariel and Umbriel have their own unique geological features. Uranus has been visited by only one spacecraft, Voyager 2, which flew by in January 1986. Voyager 2 provided the only close-up images and detailed data we have of Uranus and its moons, and much of what we know comes from that brief encounter. Since then, observations have been limited to telescopes on Earth and in orbit around Earth, and while these have revealed some new details, our understanding of Uranus remains limited compared to other planets. There's a strong scientific interest in sending another mission to Uranus, ideally an orbiter that could study the planet and its moons over a Uranian year, revealing how the extreme seasons affect the atmosphere and how the moons have evolved. Such a mission would take more than a decade to reach Uranus, but the scientific rewards could be immense, shedding light on ice giants, a class of planet that appears to be common around other stars but that we've barely explored in our own solar system. Uranus is a world of mystery, a planet tipped on its side, orbiting the Sun in its unique sideways roll. Its cold blue-green atmosphere hides a complex interior, its strange magnetic field suggests unusual dynamics, and its moons bear witness to a violent past. Uranus is a reminder that even familiar categories like gas giant and terrestrial planet don't capture the full diversity of worlds in the solar system. Ice giants like Uranus are their own category, and we've only just begun to understand them. Neptune is the 8th and most distant major planet from the Sun, a vast, cold, deep blue world orbiting in the outer reaches of the solar system. Like Uranus, Neptune is an ice giant, composed mainly of water, methane and ammonia ices surrounding a rocky core with an atmosphere of hydrogen, helium and methane. But Neptune is far more active than Uranus, with the fastest winds in the solar system, large storm systems, and a dynamic atmosphere that rivals Jupiter's in complexity. Neptune has an equatorial diameter of about 49,244 kilometers, or 30,599 miles, slightly smaller than Uranus but more massive. Neptune's mass is about 17 times Earth's mass, and its average density is about 1.64 grams per cubic centimetre, higher than Uranus, suggesting either a larger rocky core or less hydrogen and helium in the outer layers. Neptune orbits the Sun at an average distance of about 4.5 billion kilometres, or 2.8 billion miles, about 30 astronomical units. At this distance, sunlight is faint, only about 1/900th as bright as on Earth, and the temperature in the upper atmosphere is about negative 214 degrees Celsius. Yet despite being farther from the Sun than Uranus, Neptune is not as cold. This is because Neptune radiates about 2.6 times as much energy as it receives from the Sun, the excess coming from residual heat left over from the planet's formation and possibly from gravitational contraction. This internal heat drives powerful atmospheric circulation, creating the fastest winds and most active weather in the solar system. Neptune's atmosphere is similar in composition to Uranus's, dominated by hydrogen and helium, with about 2 to 3% methane. The methane absorbs red light, giving Neptune a deep blue colour, more vivid than Uranus's blue-green hue. But Neptune's atmosphere is anything but bland. When Voyager 2 flew by Neptune in 1989, it revealed a dynamic cloud-covered world with prominent bands, bright high-altitude clouds and large storm systems. The most famous feature observed by Voyager 2 was the Great Dark Spot, a massive anticyclonic storm in the southern hemisphere, similar in many ways to Jupiter's Great Red Spot. The Great Dark Spot was about the size of Earth and rotated counterclockwise with wind speeds of up to 2,000 kilometers per hour. But unlike Jupiter's Great Red Spot, which has persisted for centuries, the Great Dark Spot was short-lived. When the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, though other dark spots have since been observed to form and dissipate on Neptune. Neptune's winds are the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour, or over 1,200 miles per hour, in the upper atmosphere near the equator. These winds blow predominantly westward, in the opposite direction to Neptune's rotation, which is unusual. The exact mechanism driving these winds is not well understood, but it's thought to involve a combination of internal heat, atmospheric dynamics, and the planet's rapid rotation. Neptune rotates once every 16 hours, slightly slower than Jupiter and Saturn, but still fast enough to create significant Coriolis effects. Neptune has a magnetic field, discovered by Voyager 2, that is similar in strength to Uranus's field and similarly misaligned with the rotation axis. Neptune's magnetic field is tilted about 47 degrees relative to the rotation axis and offset from the planet's centre. This suggests that, like Uranus, Neptune's magnetic field is generated in a shell of conducting icy fluids at intermediate depths rather than in a central core. The offset and tilt create a complex asymmetric magnetosphere that wobbles as the planet rotates. Neptune has 14 known moons, the largest of which is Triton, a fascinating world with a complex history. Triton is about 2,707 kilometres in diameter, slightly smaller than Earth's moon, and it's the 7th largest moon in the solar system. Triton is unusual because it orbits Neptune in a retrograde direction, opposite to Neptune's rotation and to the orbits of the other moons. This retrograde orbit strongly suggests that Triton did not form with Neptune, but was captured from the Kuiper Belt relatively late in Neptune's history. Triton's surface is one of the coldest in the solar system, with temperatures around -235 degrees Celsius. The surface is covered with nitrogen and methane ice, and there are geysers that erupt nitrogen gas and dust particles high into the thin atmosphere. These cryovolcanic eruptions are driven by seasonal heating from the sun, which warms the surface ice and causes nitrogen to sublimate and burst through weak points in the crust. Triton's capture by Neptune would have been a violent event, with gravitational interactions heating the moon's interior through tidal flexing. Over time, Triton's orbit circularized and its rotation became tidally locked, but the internal heat may have kept the moon geologically active for hundreds of millions of years. Triton may still have a subsurface ocean beneath its icy crust, kept liquid by residual heat and radioactive decay, though this is speculative. Triton's retrograde orbit means it's gradually spiralling inward toward Neptune. In about 3.5 billion years, Triton will pass within Neptune's Roche limit, the distance at which tidal forces exceed the moon's internal gravity, and Triton will be torn apart, forming a spectacular ring system around Neptune. Neptune has a faint ring system, discovered from ground-based observations in the 1980s and confirmed by Voyager 2. The rings are narrow and clumpy, with most of the material concentrated in arc segments, rather than being uniformly distributed. The rings are composed of dark particles, possibly organic compounds darkened by radiation, and they're thought to be relatively young, formed from the breakup of small moons. Neptune has been visited by only one spacecraft, Voyager 2, in August 1989. Voyager 2's flyby provided our only close-up view of Neptune and its system, and much of what we know comes from that brief encounter. Since then, observations from the Hubble Space Telescope and large ground-based telescopes have revealed seasonal changes in Neptune's atmosphere and the occasional appearance and disappearance of storm systems, but our understanding of Neptune remains incomplete. Like Uranus, Neptune is a high-priority target for future exploration. An orbiter mission to Neptune could study the planet's dynamic atmosphere, its unusual magnetic field, and its moons, particularly Triton, which may be a captured Kuiper Belt object, and could harbour a subsurface ocean. Such a mission would help us understand ice giants, which appear to be the most common type of large planet around other stars. Neptune is the final major planet, the outermost of the 8, a world of deep blue clouds, supersonic winds, and frigid moons. It's a reminder that even at the edge of the planetary system, the solar system is full of activity and complexity. Neptune's existence wasn't predicted by ancient astronomers, but mathematical calculations of its gravitational influence on Uranus led to its discovery. A triumph of celestial mechanics, and a testament to the power of science to reveal the unseen. Beyond Neptune lies a realm of cold and darkness, a region so distant that the sun appears as little more than the brightest star in the sky. This is the outer solar system, the domain of icy dwarf planets, comets, and ancient remnants from the solar system's formation. It's a frontier we've only just begun to explore, a vast expanse that holds clues to where we came from and how planetary systems form. The Kuiper Belt is a disc-shaped region extending from about 30 astronomical units near Neptune's orbit to about 50 astronomical units from the Sun. It's similar to the asteroid belt between Mars and Jupiter, but far larger and more massive. The Kuiper Belt is populated by countless small icy bodies, mostly composed of frozen water, methane, ammonia, and other volatiles. These objects, called Kuiper Belt objects or KBOs, are remnants from the solar system's formation, planetesimals that never accumulated into a planet because the density of material was too low and Neptune's gravity stirred things up too much. The first Kuiper Belt object, other than Pluto, was discovered in 1992 by astronomers David Jewett and Jane Liu. They called it 1992 QB1, and it was just the beginning. Since then, thousands of KBOs have been discovered, and estimates suggest there may be over 100,000 objects larger than 100 kilometers in diameter in the Kuiper Belt, and trillions of smaller objects. The total mass of the Kuiper Belt is uncertain, but maybe several times the mass of the asteroid belt. Kuiper Belt objects come in different flavours. Classical KBOs have roughly circular orbits in the plane of the solar system, and are found primarily between 42 and 48 astronomical units. These are thought to be relatively undisturbed remnants from the original protoplanetary disk. Resonant KBOs are in orbital resonances with Neptune, meaning their orbital periods are simple fractions of Neptune's orbital period. The most famous of these are the Plutonos, named after Pluto, which are in a 3:2 resonance with Neptune, completing exactly 3 orbits for every 2 of Neptune's. Then there are the scattered disk objects, which have highly elliptical and inclined orbits and range much farther from the Sun. These objects are thought to have been scattered outward by gravitational interactions with Neptune during the early solar system's chaotic phase. The scattered disk extends well beyond the Kuiper Belt proper, out to hundreds of astronomical units, and it blurs into the Oort cloud, a vast spherical shell of comets that is thought to surround the solar system at distances of thousands to hundreds of thousands of astronomical units. Pluto is the most famous resident of the Kuiper Belt. Discovered in 1930 by Clyde Tombaugh, Pluto was classified as the 9th planet for 76 years. But as more KBOs were discovered, including objects comparable in size to Pluto, the definition of planet came into question. In 2006, the International Astronomical Union formally defined what constitutes a planet, and Pluto didn't quite make the cut. To be a planet, an object must orbit the Sun, be massive enough for its gravity to pull it into a roughly spherical shape, and have cleared its orbital neighbourhood of other debris. Pluto meets the first 2 criteria, but not the third. It shares its orbital zone with thousands of other KBOs, so it was reclassified as a dwarf planet. This reclassification was controversial and sparked much debate, but it reflects the reality that Pluto is one member of a large population of icy worlds beyond Neptune. Pluto's demotion doesn't diminish its scientific interest. If anything, it enhances it, because understanding Pluto helps us understand an entire class of objects. Pluto is about 2377 kilometers in diameter, slightly smaller than Earth's moon. It has a complex surface with nitrogen ice plains, mountains of water ice that rise several kilometers high, and a variety of terrains that suggest recent geological activity. Pluto's surface is mostly frozen nitrogen, methane, and carbon monoxide, which sublimate and recondense as Pluto's elliptical orbit carries it closer to and farther from the Sun. When Pluto is near perihelion, the closest point to the Sun, sublimating ices create a thin atmosphere. As it moves toward aphelion, the atmosphere freezes out and falls back to the surface. Pluto has 5 known moons. The largest, Charon, is about half Pluto's diameter, making the Pluto-Charon system almost a double dwarf planet. Charon is so large relative to Pluto that the 2 orbit a common centre of gravity that lies between them rather than inside Pluto. Pluto and Charon are tidally locked to each other, each always keeping the same face toward the other. The other 4 moons, Styx, Nix, Kerberos and Hydra, are much smaller and orbit farther out. In July 2015, NASA's New Horizons spacecraft flew past Pluto, providing the first close-up images and data from this distant world. The images revealed a complex geologically active surface far more interesting than anyone had expected. There are vast plains of nitrogen ice, apparently churned by slow convection in the deep ice. There are mountains of water ice as tall as the Rockies. There are possible cryovolcanoes, regions where water ice mixed with ammonia and methane may have erupted onto the surface. Pluto's heart-shaped region, informally named Tombor Regio, is a vast ice plain that may be less than 10 million years old, astonishingly young for a world so far from the Sun. The New Horizons data suggested that Pluto may have a subsurface ocean of liquid water beneath its icy crust, kept liquid by heat from radioactive decay in the core and by insulation from the ice above. If true, this would make Pluto another potential abode for life, though the conditions would be harsh and the chances of life actually existing there are very slim. After the Pluto flyby, New Horizons continued deeper into the Kuiper Belt and flew past another KBO on January 1st, 2019. This object, initially designated 2014 MU69 and later named Arrokoth, is a small, reddish contact binary object, meaning it's two lobes that have gently merged together. Arrokoth is much smaller than Pluto, only about 36 kilometers long, and it's one of the most primitive objects ever visited by a spacecraft, essentially unchanged since the solar system's formation. Its gentle merger suggests that the process of planetary accretion in the outer solar system was slow and gentle rather than violent, providing important clues about how planets form. Other large KBOs include Haumea, Makemake, and Quaoar, all classified as dwarf planets or candidates. Haumea is particularly strange, shaped like an elongated football due to its rapid rotation, and it has a ring system, one of the few small bodies known to have rings. Makemake is comparable in size to Pluto and has at least one moon. Quaoar is slightly smaller and also has a ring system. These objects, along with Pluto, represent the largest of the KBOs discovered so far, but there may be others of similar size waiting to be found. The scattered disk object Eris, discovered in 2005, is about the same size as Pluto and slightly more massive. Its discovery was one of the triggers for the planet definition debate that led to Pluto's reclassification. Eris orbits far beyond the Kuiper Belt proper, with a highly elliptical orbit that takes it from about 38 astronomical units at closest approach to about 98 astronomical units at its farthest. Beyond the Kuiper Belt and scattered disk at distances so great that they are almost incomprehensible lies the Oort cloud. The Oort cloud has never been directly observed. It's too far away and the objects in it are too faint. But the existence of the Oort cloud is inferred from the orbits of long-period comets that take thousands or millions of years to orbit the Sun and enter the inner solar system from seemingly random directions. These comets must have a source, and the most plausible source is a vast shell of icy bodies surrounding the solar system, stretching from perhaps 5,000 to 100,000 astronomical units from the Sun, possibly even farther. The Oort cloud is thought to contain trillions of comets, each one a small icy world, typically just a few kilometers across. These comets formed closer to the Sun, probably in the region of the giant planets, but were gravitationally scattered outward during the early solar system's chaotic phase. They now reside at the very edge of the Sun's gravitational influence, in a region where the gravity of nearby stars can perturb their orbits and send them falling back toward the inner solar system, where they heat up, develop tails, and become the spectacular comets that have captivated humans for millennia. The Oort cloud marks the edge of the solar system in a real sense. Beyond it, the Sun's gravity becomes so weak that it's comparable to the gravitational influence of other stars in the galaxy. Objects beyond the Oort cloud are not gravitationally bound to the Sun and drift in the interstellar medium. The boundary between the solar system and interstellar space is gradual, not sharp, but the Oort cloud is as good a boundary as any. The outer reaches of the solar system are a realm of discovery. We've sent just one spacecraft, New Horizons, to explore the Kuiper Belt, and it's visited only 2 objects. There are thousands more waiting to be explored. Future missions could target other dwarf planets like Eris or Haumea, or explore the diversity of KBOs in different dynamical classes. Each object is a time capsule, preserving material and information from the solar system's formation 4.5 billion years ago. Understanding the outer solar system helps us understand how planetary systems form and evolve. The Kuiper Belt and Oort cloud are reservoirs of primitive material, largely unchanged since the solar system's youth. Comets, which originate from these regions, occasionally fall inward and deliver water, organic molecules, and other compounds to the inner planets. Earth's oceans, and perhaps even the building blocks of life, may have been delivered by comets billions of years ago. The outer solar system also helps us understand planets around other stars. Ice giant planets like Uranus and Neptune, and smaller ice worlds like Pluto, appear to be common in other planetary systems. By studying our own ice giants and Kuiper Belt, we're learning about a category of world that may dominate the exoplanet population. The edge of the solar system is not a wall but a frontier, a gradual transition from the sun's domain to the cold, dark expanse of interstellar space. Beyond Neptune, beyond the Kuiper Belt, beyond the Oort cloud, lie the stars, billions and billions of them in our galaxy alone, many with their own planetary systems, their own Jupiters and Saturns and Earths. The solar system is just one of countless systems, a small corner of a vast universe, but it's our corner, our home, and it's a place of endless wonder and discovery. And so, we've journeyed together through the solar system, from the sun's blazing core to the frozen darkness of the Oort cloud, from the scorched surface of Mercury to the icy geysers of Enceladus and Triton. We've witnessed gas giants with centuries-old storms, ice giants tipped on their sides, terrestrial worlds that might once have harboured life, and a blue marble teeming with life in all its glorious diversity. The solar system is more than just a collection of objects orbiting a star. It's a family, a system born from chaos and sculpted by gravity, chemistry and chance. It's a laboratory where we can study planetary formation, atmospheric dynamics, geology, and even the potential for life beyond Earth. It's our home on the larger scale, the only corner of the universe we can currently reach with spacecraft, and the only place where we know for certain that life exists. Every world in the solar system has a story. Mercury tells us about extreme environments and the role of distance from the Sun. Venus warns us about runaway greenhouse effects and the delicate balance of planetary climates. Earth shows us that life can emerge and thrive given the right conditions, turning a rocky ball into a vibrant biosphere. Mars hints that planets can change dramatically over time, losing their atmospheres and surface water, but perhaps retaining pockets of habitability below the surface. Jupiter reminds us that planets can be utterly different from Earth, yet still follow the same physical laws, creating beauty and complexity from simple ingredients like hydrogen and helium. Saturn's rings teach us about gravitational interactions, orbital mechanics, and the artistry of nature. Uranus and Neptune show us that ice giants are their own unique category, with strange magnetic fields, supersonic winds and moons that may once have been independent worlds. The small bodies, the asteroids and comets and Kuiper Belt objects, are messengers from the past, carrying information about the solar system's formation and evolution. Pluto, reclassified but not forgotten, is a world as geologically active as many planets despite its small size and frigid temperatures. The moons of the solar system, dozens of them, are often as interesting as the planets they orbit, with subsurface oceans, active geology, and diverse compositions. As you drift off to sleep tonight, think about the fact that everything around you, every atom in your body, was forged in the heart of stars that lived and died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created through nuclear fusion in stellar cores or in the explosive deaths of massive stars. We are quite literally made of stardust, and we live on a world that orbits a star in a galaxy filled with hundreds of billions of other stars, each one a potential sun to its own family of worlds. The solar system is vast, but it's just the beginning. Beyond the Oort cloud lie the stars, and beyond our galaxy lie billions of other galaxies, each containing billions of stars, many with their own planets. The universe is unimaginably large, and we're only just starting to explore it. But the solar system is our starting point, our home, and understanding it is the first step in understanding the cosmos as a whole. Before you close your eyes, take a moment to appreciate the journey we've taken tonight. We've travelled billions of kilometres without leaving your bed, witnessed wonders that would have been unimaginable to our ancestors, and explored worlds that, until very recently, were just points of light in the sky. We live in an age where spacecraft explore distant moons, telescopes peer into the atmospheres of exoplanets, and our understanding of the universe grows with each passing year. If you enjoyed tonight's journey through the solar system, please consider liking this video and subscribing to Science Sleep Stories. It helps us continue creating these cosmic voyages, these relaxing explorations of science and space. Let me know in the comments what you'd like to explore next, what mysteries of the universe fascinate you most. And thank you for joining me tonight. The solar system awaits, vast and beautiful, complex and ancient, a testament to the power of gravity, chemistry, and time to create order from chaos. It's been spinning around the sun for 4.5 billion years, and it will continue spinning for billions more. We're privileged to live in this moment, to witness this small part of its story, to be conscious stardust capable of understanding and appreciating the cosmic dance. Sweet dreams, and may your sleep be filled with visions of distant worlds, glittering rings, and the endless beauty of the cosmos. Good night.